470 million years ago, the Earth was an ocean world. Not the ocean world you know, not the familiar arrangement of Atlantic and Pacific, Mediterranean and Caribbean, continents standing firm against the waves. The Ordovician Earth had drowned. Sea levels stood 600 meters higher than today, and the difference was catastrophic for dry land. Shallow seas had invaded the continental interiors, spreading across lowlands, filling basins, converting what should have been solid ground into endless expanses of warm, sunlit water. From orbit, the planet would have looked profoundly alien. The northern hemisphere was almost entirely ocean, a vast blue emptiness broken only by scattered island arcs and the occasional volcanic peak. The southern hemisphere held more land, but even there, the supercontinent of Gondwana, future Africa, South America, Antarctica, Australia, and India, all fused together, lay partially submerged, its margins drowned, its interior crossed by seaways that connected distant shores. The familiar continents did not exist. North America was Laurentia, a craton straddling the equator, rotated 45 degrees from its modern orientation, almost entirely underwater. Europe was Baltica, drifting in the southern tropics, separated from Laurentia by the Iapetus Ocean, a body of water that would close over the next 200 million years, its destruction building the Appalachians and the mountains of Scotland and Scandinavia. Siberia floated alone in the Northern Ocean. China existed as scattered terrains, microcontinents not yet assembled into their modern configuration. The geography was alien. The climate was extreme. Early in the Ordovician, atmospheric carbon dioxide reached 7,000 parts per million. The number requires context. Modern CO2 levels hover around 420 parts per million, and this concentration is already warming the planet, melting ice caps, raising seas. The Ordovician had nearly 17 times more carbon dioxide in its atmosphere. The greenhouse effect was overwhelming. Sea surface temperatures in the tropics may have exceeded 45 degrees Celsius, 113 degrees Fahrenheit. Modern coral reefs bleach and die when temperatures rise a degree or two above normal. The Ordovician tropics were a thermal extreme, a zone where only specialized organisms could survive, where the water itself approached the limits of what complex life could tolerate. The poles were ice-free. No glaciers, no ice caps, no frozen seas. Warmth reached from equator to pole, moderating temperature gradients, creating a world without the sharp climatic zones that characterize modern Earth. Antarctica, or rather the portion of Gondwana that would become Antarctica, was temperate, perhaps even warm, its shores lapped by waters that would have seemed comfortable to a modern swimmer. This was a greenhouse world, one of the warmest intervals in the past 500 million years. Life had adapted to heat before, and it would adapt again. The organisms of the Ordovician were not suffering. They had evolved under these conditions, their metabolisms tuned to temperatures that would kill their modern descendants. What seems extreme to us was simply normal to them. The heat would not last. Somewhere in the middle of the period, the climate began to shift. Carbon dioxide levels dropped from 7,000 parts per million to perhaps 4,000. The cause remains debated. Volcanic activity may have slowed, reducing CO2 emissions. The weathering of newly uplifted mountains may have accelerated, drawing carbon from the atmosphere. Or perhaps the first land plants, just beginning their tentative colonization of the continents, had started to make a difference, their photosynthesis and their enhancement of rock weathering beginning to cool the planet. Whatever the cause, the cooling was real. The Middle Ordovician was more temperate than its beginning. The Late Ordovician would be colder still. The shallow seas were the key to everything. When ocean water floods a continent, it creates something special. The water is shallow, tens of meters, not thousands. Sunlight penetrates to the bottom. Nutrients wash in from the exposed land. The seafloor becomes a garden, a substrate where life can anchor, build, grow. These epicontinental seas were vast. Imagine the Mediterranean, but stretching across the entire interior of North America. Imagine the Caribbean, but covering the Sahara. The scale was almost incomprehensible. Millions of square kilometers of warm, productive, well-lit marine habitat, more than the modern Earth possesses, more than had existed in the Cambrian, perhaps more than would exist ever again. The organisms that filled these seas were the inheritors of the Cambrian explosion. 50 million years earlier, animal life had diversified with unprecedented speed, producing all the major body plans, the phyla, that would persist to the present day. Arthropods, mollusks, echinoderms, brachiopods, chordates, the fundamental architectures of animal existence had been established in that first great radiation. The Ordovician would do something different. It would take those body plans and multiply them. Not new phyla, but new classes, new orders, new families, new genera, new species. The Cambrian had drawn the blueprints. The Ordovician would build the city. Marine animal diversity roughly tripled during this period. The number of families increased from around 100 to nearly 500. Every major group of marine invertebrate radiated, filling ecological niches that the Cambrian had left empty. Brachiopods diversified into forms that would dominate seafloors for the next 200 million years. Bryozoans appeared for the first time, their colonial architecture adding new complexity to reef ecosystems. Cephalopods grew large, grew predatory, grew into the apex hunters of their age. Trilobites, already diverse, became more diverse still, evolving bizarre spines and enormous eyes and bodies adapted for swimming, burrowing, hunting, hiding. Scientists call this the Great Ordovician Biodiversification Event, the GOBE. The term was formalized in the 1990s, the product of an international research program that brought together paleontologists from around the world to document what had happened. The GOBE was not a single event, not a moment, but a sustained radiation lasting tens of millions of years, the cumulative result of countless evolutionary experiments unfolding across the flooded world. The Cambrian explosion is famous, the GOBE is not. This is an injustice of popular science because in terms of sheer diversity increase, the number of new forms, the ecological transformation of the oceans, the Ordovician radiation was larger. The Cambrian invented the toolkit. The Ordovician showed what the toolkit could build. The man who gave this period its name was trying to end a war. Charles Lapworth was a Scottish schoolteacher turned geologist, working in the hills of Wales in the 1870s. He had stumbled into the middle of a vicious dispute. Two giants of British geology, Adam Sedgwick and Roderick Murchison, had spent decades fighting over who owned certain rock layers. Sedgwick claimed them for his Cambrian system. Murchison claimed the same rocks for his Silurian. The argument had grown personal, bitter, a stain on the reputation of Victorian science. Lapworth examined the fossils. He studied the graptolites, those strange colonial organisms whose remains filled the black shales of Wales, their delicate patterns like writing on stone. The name means written stone in Greek. He noticed something that Sedgwick and Murchison, locked in their territorial dispute, had overlooked. The fossils in the contested rocks were different from the Cambrian below, different from the Silurian above. These rocks contained their own distinct fauna, organisms that marked a separate chapter in the history of life. In 1879, Lapworth proposed a compromise. He carved out a new period, named it for the Ordovices, a Celtic tribe that had once inhabited northern Wales, and inserted it between the warring systems. The Ordovician was born from diplomacy, from a schoolteacher's careful observation of fossils that the professors had been too busy arguing to see clearly. The international geological community did not officially recognize the Ordovician until 1960, 40 years after Lapworth's death. Science moves slowly. Good ideas take time. But Lapworth was right. The Ordovician was distinct, a world unto itself, a chapter in Earth's history that deserved its own name. You are entering a world older than imagination can easily grasp. The Ordovician ended 443 million years ago. The dinosaurs would not appear for another 200 million years after that, and they would rule for 165 million years, and then they would be gone for 66 million years, and only then would anything resembling a human walk the Earth. The Ordovician is not ancient by comparison to the dinosaurs. It is ancient by comparison to the concept of ancientness itself. Yet the rocks remember, the fossils preserve what lived. The limestones that built the pyramids of Egypt formed on Ordovician seafloors, the compressed remains of countless shells, the calcium carbonate of organisms that filtered the warm shallow seas and died and drifted down and became stone, the marble of Greek temples, the building stones of medieval cathedrals, the flagstones beneath your feet in old European cities. Ordovician. The period lasted 42 million years. In that time, life transformed. The oceans filled with forms that had never existed before. The land, still barren, began to receive its first colonizers. The climate shifted from greenhouse to something cooler, setting up conditions for catastrophe at the period's end. The seas are warm, the continents are drowned. Sunlight still reaches the seafloor, and in that wide, shallow brightness, life is no longer scattered, it's busy. Everywhere you look, something is growing, filtering, hunting, hiding, adapting. We have entered the Ordovician. For the first time in a long time, the ocean feels like it has space to spare, warm, well lit, and rich with nutrients. And when the stage changes, the rules change with it. The Cambrian had drawn the blueprints, but blueprints are not buildings. Now the empty rooms of these flooded seas were ready to be occupied, and life began running experiments at scale, filtering, hunting, hiding, multiplying. This surge became so dramatic it earned a formal name, the Great Ordovician Biodiversification Event. And names like that don't get invented for a slow drift. They get invented for a moment you can feel in the record, a real turn in the story. If you want proof, look at the count. Early in the Ordovician, the oceans held on the order of a few hundred genera of marine animals, perhaps around 450. By the middle of the period, that figure had multiplied. Roughly 1,400 genera, each a distinct branch on the tree of life, all sharing seas that had spread across the drowned continents. Few intervals in Earth's history show a rise in marine diversity this sustained and this intense. The Cambrian explosion, tens of millions of years earlier, had introduced the major body plans. The Ordovician made them flourish. Where the Cambrian sketched an outline, the Ordovician filled in the details. Niche by niche, coastline by coastline, until the shallow oceans felt crowded with possibility. The paleontologists who first recognized this pattern struggled to name it. The Cambrian explosion had captured the public imagination, its dramatic name conjuring images of sudden creation, of life bursting forth from nothing. The Ordovician radiation was less photogenic, harder to summarize, more difficult to explain. It was not an explosion. It was something slower, more sustained, more pervasive, a great swelling of diversity that transformed the oceans over tens of millions of years. In 1995, an international research program set out to document what had happened. Led by Barry Webby, an Australian paleontologist at Macquarie University, the project brought together scientists from around the world, each contributing data on different fossil groups, different time intervals, different regions. The synthesis took nearly a decade. When Webby published the results in 2004, he gave the event its formal name, the Great Ordovician Biodiversification Event. The acronym followed inevitably, GOBE. Paleontologists love acronyms, and this one stuck. The GOBE entered textbooks, conference presentations, research papers. The Ordovician radiation finally had a name to rival the Cambrian explosion. Why did it happen? The question has occupied researchers for decades, and the honest answer is that no one knows for certain. The GOBE was not caused by any single factor. It emerged from a confluence of conditions, geological, climatic, biological, that together created an opportunity without precedent. The paleogeography helped. With continents scattered across the globe, separated by deep ocean basins, there was enormous diversity of habitat. The tropical shelves of Laurentia were different from the tropical shelves of Baltica, which were different from the temperate margins of Gondwana. Each region developed its own fauna, its own evolutionary experiments, its own solutions to the problems of survival and reproduction. When occasional connections formed, through shifting currents, through the closure of seaways, through the drift of continents, successful innovations spread, mixing with local forms, creating new combinations. The extent of shallow seas mattered. More shelf area meant more habitat, more space for organisms to occupy, more ecological niches to fill. The drowned continents of the Ordovician provided the largest tropical shelf area of the entire Phanerozoic, the last 540 million years of Earth history. The real estate was available. Life moved in. The climate shift may have been crucial. The extreme greenhouse conditions of the early Ordovician gave way to cooler temperatures in the middle of the period. Cooler water holds more dissolved oxygen. More oxygen means organisms can grow larger, can be more active, can sustain the metabolic demands of predation and rapid movement and complex behavior. The cooling may have opened possibilities that the earlier hothouse had foreclosed. Oxygen levels in the atmosphere and ocean were rising. The precise trajectory remains debated, but evidence suggests that the Ordovician saw a significant increase in available oxygen, perhaps crossing thresholds that allowed new metabolic strategies, new body sizes, new ecological interactions. An animal that needs to breathe cannot evolve in an ocean where there is nothing to breathe. The Ordovician ocean, increasingly oxygenated, removed that constraint. And there were ecological feedbacks, cascades of interaction that amplified the initial diversification. New predators created pressure for new defenses. New filter feeders opened resources that bottom dwellers could not access. New burrowers altered the seafloor, creating microhabitats that other organisms could exploit. Each innovation enabled others. The diversification fed on itself. The transformation was not merely a matter of numbers. The structure of marine ecosystems changed fundamentally. In the Cambrian, most animals lived on or in the seafloor. They crawled across the sediment surface, burrowed into the top few centimeters of mud, grazed on bacterial mats, scavenged organic particles. The water column above was largely empty, unexploited, a three-dimensional space that almost nothing had learned to occupy. The Ordovician changed this. Animals began to build upward. Crinoids, sea lilies, relatives of starfish and sea urchins, anchored themselves to the bottom and extended long stalks topped with feathery arms, filtering food particles from the water column. Some reached heights of a meter or more, their arms waving in the currents, capturing plankton and organic debris that drifted past. Where crinoids grew densely, they created underwater meadows, their stalks swaying like grass in an unseen wind. Bryozoans appeared for the first time, colonial animals that built calcium carbonate skeletons in branching, encrusting, or lacy forms. Some grew upright, adding vertical structure to the seafloor. Others encrusted hard surfaces, shells, rocks, the stalks of crinoids, creating three-dimensional habitats where other organisms could shelter. Brachiopods, already present in the Cambrian, radiated into hundreds of new forms. Most were filter feeders, drawing water through their shells, extracting food particles, expelling waste. They carpeted the sea floor in some environments, their shells packed so densely that the sediment beneath them was almost invisible. Corals began to build reefs, not the coral reefs of modern tropical seas. Those are built by different animals, scleractinian corals that would not evolve for another 200 million years. The Ordovician reefs were constructed by tabulate and rugose corals, by stromatoporoids, by bryozoans and sponges and organisms whose names are known only to specialists. These reefs were smaller than modern ones, less architecturally complex, but they were reefs nonetheless, three-dimensional structures rising above the seafloor, creating shelter, breaking currents, concentrating life. The Cambrian seafloor had been relatively flat, relatively simple, its communities organized in two dimensions. The Ordovician seafloor was tiered, layered, organisms stacked above organisms, each level filtering different water masses, each exploiting different resources. The ecological structure that would dominate marine environments for the next 250 million years, the Paleozoic evolutionary fauna, in the terminology of paleontologist Jack Sepkoski, was established in the Ordovician and refined thereafter. The diversification was not uniform. Different groups radiated at different times, in different places, at different rates. The earliest phase, in the late Cambrian and earliest Ordovician, saw the diversification of plankton, the tiny organisms that drift in the water column, forming the base of marine food webs. Acritarchs, the organic walled cysts of unknown algae, became more diverse. Chitinozoans, mysterious flask-shaped microfossils that may have been the eggs of some larger organism, appeared and spread. Graptolites, colonial animals that dangled from floating structures, began their radiation. The planktonic diversification mattered because plankton are food. More diverse plankton meant more resources for the animals that ate them, whether filter feeders straining particles from the water or predators hunting the larger planktonic forms. The base of the food web expanded, and everything above it expanded in response. The middle phase, from the early to middle Ordovician, saw the diversification of bottom-dwelling communities. Brachiopods radiated. Bryozoans appeared and spread. Trilobites evolved new forms, new feeding strategies, new ways of sensing and avoiding predators. Gastropods, snails and their relatives, became more diverse, more abundant, grazing on the bacterial films and algae that coated hard surfaces. The late phase, from the middle to late Ordovician, saw the diversification of reef communities. Corals and stromatoporoids built larger structures, more complex frameworks, environments where hundreds of species could coexist. The ecological complexity of Ordovician reefs approached, though never quite matched, the complexity of modern coral reefs. Throughout all phases, cephalopods were diversifying. These would become the apex predators of the Ordovician seas, and their story deserves its own telling. The GOBE was not unique to any region. It happened everywhere, on every continent, in every ocean basin. The pattern varied locally. Different groups dominated different areas. Different innovations arose in different places, but the overall trajectory was global. Marine diversity increased on Laurentia, on Baltica, on Gondwana, in the Iapetus Ocean and the Panthalassic Ocean and the smaller seas between. This global synchrony has puzzled researchers. If the GOBE were driven purely by local factors, by the peculiarities of this shelf or that basin, You would expect different regions to diversify at different times in response to different conditions. The rough synchrony suggests something more fundamental, some global trigger or enabling condition that affected the entire planet. The leading candidates are the ones already mentioned. The paleogeographic configuration, with its vast shelf areas and isolated basins. The climatic cooling, with its oxygen enrichment. The ecological cascades, with their feedback loops. Perhaps all of these contributed. Perhaps there were factors we have not yet identified, triggers buried in the geological record that future research will reveal. The Ordovician kept secrets for 500 million years. It continues to yield them, slowly, one fossil at a time, one chemical analysis at a time, one careful study at a time. In southern France, in the region called Montagne Noire, amateur paleontologists Eric Monserrat and Sylvie Monserrat-Goujon had been searching for fossils since their 20s. Decades of weekends spent hiking the hills, scanning outcrops, splitting rocks with patient hammer blows. They knew the geology of their region as intimately as they knew their own neighborhood. In the early 2020s, they found something extraordinary. The rocks were early Ordovician, approximately 470 million years old. The preservation was exceptional, not just shells and hard parts, but soft tissues, digestive systems, cuticles, structures that normally decay within days of death. 400 fossils emerged from a single site, each one a window into an ecosystem that had existed near the South Pole when Gondwana straddled the bottom of the world. Scientists from the University of Lausanne analyzed the discovery. The results, published in Nature Ecology and Evolution in February 2024, revealed a fauna unlike any previously known from the early Ordovician. Arthropods, cnidarians, sponges, algae. The diversity was stunning, the preservation museum quality. The site was named the Cabrieres Biota, after the nearby village. The Cabrieres Biota matters because it shows that the GOBE was not limited to tropical environments. Even near the poles, in waters that would have been cooler than the equatorial furnace, life was diversifying, experimenting, filling niches. The radiation was truly global, reaching from the hottest tropics to the coldest high latitudes. Eric and Sylvie Monserrat had spent their lives looking at rocks. They had developed the patience that paleontology requires, the willingness to search for years without finding anything significant, the persistence to keep searching anyway. When they finally found the Cabrieres Biota, they recognized its importance immediately. "We went from amazement to excitement," Sylvie said in an interview after the discovery was announced. The scientific community went through the same transition, only slower, waiting for the peer review, the analyses, the confirmation that this was real. The rocks of Montagne Noire had kept their secret for 470 million years. The Monserrat family, with their hammers and their patience, had finally convinced them to speak. The shallow seas of the Ordovician were diversifying faster than any ocean before or since. The GOBE was rewriting the rules of marine ecology, building the tiered communities that would dominate the next 250 million years. And somewhere in those crowded waters, moving through forests of crinoids, hunting across fields of brachiopods, something was growing large. Something with tentacles, something with a beak, something that would become the first true apex predator the oceans had ever known. The fossil was larger than a serving platter. 72 centimeters from head to tail, its body preserved in the fine-grained limestone of what is now Manitoba, Canada. The creature had died 450 million years ago on the floor of a shallow tropical sea, and the sediment had buried it gently, completely, preserving every segment of its articulated exoskeleton. When paleontologists finally extracted it from the rock in 1998, they realized they were looking at the largest complete trilobite ever found. They named the species Isotelus rex, the king. The name was appropriate. Isotalus rex was a giant among trilobites, a predator that had roamed the seafloors of Ordovician Laurentia, using its broad, shovel-shaped head to plough through sediment, hunting worms and other soft-bodied prey. Its eyes, mounted on raised stalks, could scan the environment for threats and opportunities. Its body, smoothly curved and heavily calcified, was built for power rather than speed. Ohio adopted Isotalus as its state fossil in 1985, a recognition that these creatures were once abundant in the shallow seas that covered the American Midwest. You can find their remains today in the limestones of the Cincinnati region, in the building stones of old houses, in the road cuts along highways. The kings are everywhere if you know how to look. Isotalus rex was exceptional in size, but not in kind. The Ordovician was the golden age of trilobites, a period when these arthropods reached their maximum diversity, their greatest ecological range, their most elaborate morphological experimentation. More than 22,000 species have been described from the fossil record, and the Ordovician contained a substantial fraction of them. Trilobites had been evolving for 50 million years before the Ordovician began. They first appeared in the early Cambrian, already diverse, already differentiated into distinct lineages. Their origin remains mysterious. The earliest trilobites appear in the fossil record fully formed, with no obvious transitional forms linking them to earlier arthropods. Somewhere in the late Ediacaran or earliest Cambrian, the trilobite body plan emerged, and within a few million years, these animals had spread across the world's oceans. The body plan was simple and effective. A trilobite was divided into 3 lobes running lengthwise, hence the name, and into 3 sections from front to back: the cephalon, head, the thorax, body, and the pygidium, tail. The exoskeleton was made of calcite, the same mineral that forms limestone, which is why trilobites fossilize so beautifully. When a trilobite died, its calcite shell was already halfway to becoming rock. The Cambrian trilobites were successful, but they were also limited. Most were deposit feeders, eating organic particles from the seafloor. Most were relatively small, a few centimeters long. Most had similar body shapes, similar lifestyles, similar ecological roles. The Ordovician would change all of this. As the GOBE transformed marine ecosystems, trilobites transformed with them. They evolved new feeding strategies, new sensory systems, new defensive mechanisms, new ways of moving through the water and across the seafloor. The conservative Cambrian forms gave way to an explosion of experimentation. Some trilobites learned to swim. The Ordovician oceans contained trilobites that had abandoned the seafloor entirely, evolving into pelagic forms that cruised through the water column like modern krill. These swimming trilobites had large eyes, enormous eyes sometimes, that wrapped around their heads, providing nearly 360-degree vision. Their bodies were streamlined, their lateral lobes reduced to minimize drag. They had evolved to live in open water, far from the bottom, hunting smaller organisms or filtering particles from the currents. Carolinite genesinica was one of these swimmers. Its fossils have been found across the globe, in the United States, in the Arctic, in Siberia, in Australia, in China, a distribution spanning the entire equatorial realm of the Ordovician world. No bottom-dwelling trilobite achieved such cosmopolitan range. Carolinites could go wherever the currents carried it, wherever the water was warm enough, wherever food was available. The entire tropical ocean was its habitat. The pelagic trilobites may have filled ecological roles similar to modern krill, forming dense swarms in productive waters, providing food for larger predators. They were part of the Ordovician revolution in the water column, the filling of 3-dimensional space that had been largely empty in the Cambrian. Other trilobites went the opposite direction. burrowing deeper into the sediment than their ancestors had managed. Trilobites with shovel-shaped heads evolved to push through mud, hunting in faunal worms, exploiting resources that surface dwellers could not reach. The sediment itself became a habitat, a place to hide, a place to hunt, a place to make a living invisible to the world above. The predators were evolving, and the trilobites had to keep up. The Ordovician seas contained dangers that the Cambrian had not known. Cephalopods were growing large, growing fast, growing hungry. Eurypterids, sea scorpions, were appearing in the fossil record, armed with grasping appendages and compound eyes. Starfish had evolved, their tube feet capable of prying open shells, their stomachs capable of digesting prey outside their bodies. For a trilobite, the world was becoming more dangerous with every passing million years. The response was armor, spines, elaborate ornamentation that made trilobites difficult to swallow, painful to bite, expensive to attack. Some trilobites evolved spines so long and elaborate that they seem almost absurd, their bodies bristling with projections that would have deterred any predator unable to find a safe angle of attack. Selena peltis, from the Ordovician of Europe and North Africa, carried spines that extended far beyond its body in multiple directions, a defensive architecture that made the animal look more like a medieval weapon than a living creature. Others evolved the ability to roll their bodies into tight balls, tucking their soft undersides beneath the protective dome of their exoskeletons. Enrollment was not new. Some Cambrian trilobites could do it. But the Ordovician saw the perfection of the technique, the evolution of interlocking mechanisms that allowed trilobites to seal themselves completely, presenting a smooth calcite sphere to any would-be predator. Flexically mean, common in the Ordovician rocks of Ohio and surrounding states, was a masterful enroller. Its fossils are often found in the enrolled position, curled tight, preserved in the defensive posture that had served it in life. Whether the animal had enrolled in response to a threat and then been buried by sediment, or whether it had simply died while resting in its default protective stance, the fossil record does not reveal. What it does reveal is that enrollment worked well enough to be preserved across millions of specimens. The eyes of trilobites were among the most sophisticated visual systems the world had ever produced. Trilobite eyes were compound, like the eyes of modern insects and crustaceans, composed of multiple individual lenses packed together into a curved array. But unlike insect eyes, which use soft organic lenses, trilobite eyes were made of calcite, crystalline calcium carbonate, the same mineral as their shells. These were eyes made of stone, lenses that could fossilize, preserving the optical systems of animals dead for hundreds of millions of years. The calcite lenses posed a problem. Calcite is birefringent. It splits light into two rays, creating double images. Any simple calcite lens would produce blurred, duplicated vision, useless for an animal trying to detect predators or locate prey. The trilobites solved this problem with an elegance that would not be rediscovered by human scientists until the 17th century. The lenses were oriented with their crystalline axes aligned to minimize birefringence. In some species, the lenses were corrected with a second layer of chitin that compensated for the remaining distortion. The trilobites had invented achromatic doublets, corrected lenses that produced sharp images, hundreds of millions of years before Christian Huygens and René Descartes worked out the principles of lens correction. Some Ordovician trilobites had eyes mounted on stalks, raised above the body like periscopes. Asaphus Koalevsky, from the Ordovician of Russia, had eye stalks so tall that it could bury its body in sediment and still see the world above, watching for predators, watching for prey, watching and waiting with infinite patience. Others had lost their eyes entirely. In the deep ocean, in cave systems, in any environment where light did not penetrate, eyes were useless. a metabolic expense with no return. Blind trilobites evolved repeatedly, their eye surfaces smooth and featureless, their other senses presumably enhanced to compensate for the darkness. The trilobites of the Ordovician were not merely numerous and diverse, they were everywhere. Walk into a museum with an Ordovician fossil collection and trilobites will dominate the displays. Visit a fossil shop and Ordovician trilobites will fill the shelves. Elrathia from Utah, Phacops from Morocco, Calamine from Britain, Isotellus from Ohio. They are the most recognizable fossils of the Paleozoic, the creatures that define the era in the popular imagination. Their abundance in collections reflects their abundance in life. Trilobites were among the most common animals in Ordovician seas, present in almost every marine environment, filling roles from scavenger to predator, from plankton feeder to deposit muncher. A typical Ordovician seafloor community contained multiple trilobite species, each occupying a different niche, each avoiding competition with the others through subtle differences in diet, behavior, and microhabitat. The diversity could be staggering. Some single localities have yielded dozens of trilobite species living contemporaneously, sharing the same patch of seafloor, somehow partitioning the resources finely enough that all could coexist. The mechanisms of this coexistence remain partially mysterious. We can see that it happened, but reconstructing the ecological details from fossils 500 million years old requires inference, imagination, careful analysis of feeding structures and trace fossils and sedimentary context. What we know is that the Ordovician trilobites had solved the problem of coexistence. They had learned to share a world that was becoming increasingly crowded. The crowding would not last. At the end of the Ordovician, catastrophe struck. The mass extinction that closed the period was the second largest in Earth's history, and it hit trilobites hard. Entire families vanished. Entire ecological guilds disappeared. The swimmers, the burrowers, the spine-bearers, the stalk-eyed predators, all were decimated, their diversity collapsing, their dominance ending. Trilobites survived the extinction. They would continue for another 200 million years, finally disappearing at the end of the Permian. But they never recovered their Ordovician glory. The post-Ordovician trilobites were a diminished group, less diverse, less ecologically dominant, increasingly marginalized as other arthropods, crustaceans, chelicerates, rose to prominence. The Ordovician was their peak, the moment when trilobites ruled the seafloor, when their armored bodies carpeted the benthos of every continent, when their crystalline eyes scanned waters from pole to equator. They had been evolving for 50 million years when the period began. They had another 250 million years ahead of them. But the Ordovician was the summit, the high point from which everything afterward was a long, slow descent. The trilobites were lords of the seafloor. They shared that seafloor with brachiopods and bryozoans, with crinoids and corals, with worms and snails and nameless, soft-bodied creatures that left no fossils. They competed for food, for space, for survival, and they looked up sometimes with their crystalline eyes into the water column above. Something was moving there, something large, something with tentacles trailing behind it, with a shell like a spear, with a beak that could crack calcite armor as easily as you might crack an egg. The trilobites were not the only lords of the Ordovician seas. 6 meters of shell pointed like a spear. The animal inside was a cephalopod, a relative of modern squid and octopus, but it looked nothing like its soft-bodied descendants. Its body occupied only the largest chamber at the open end of that immense cone. Behind it stretched meter after meter of empty shell, divided into compartments by curved walls called septa, each chamber connected to the animal's body by a thin tube of tissue called the siphuncle. Through this tube, the cephalopod could adjust the gas content of its chambers, regulating buoyancy, rising and sinking through the water column, with minimal effort. The genus was Endoceras. Its fossils have been found across the world, in North America, in Europe, in China, in Australia, the scattered remains of a predator that once dominated the Ordovician seas. The largest confirmed specimen measures 3 meters as preserved, but the shell is incomplete, broken at its narrow end. Reconstructions suggest the full animal approached 6 meters in length. Unconfirmed reports describe specimens even larger, approaching 9 meters, though these claims remain controversial. Endoceras was the largest animal the Earth had ever produced, larger than any Cambrian organism, larger than the giant anomalocaridids that had hunted the earlier seas. For the first time in the history of life, something truly enormous swam through the oceans, something that could eat anything it encountered, something against which even the armored trilobites had limited defense. The age of giant cephalopods had begun. Cephalopods evolved in the late Cambrian, descended from some crawling, snail-like ancestor that learned to secrete a chambered shell. The key innovation was buoyancy control. A snail carries its shell as dead weight, dragging it across the seafloor, limited to crawling speeds, limited to bottom-dwelling existence. The early cephalopods discovered that by sealing off portions of their shells and filling them with gas, they could float. The shell became a flotation device rather than a burden. The animal could rise into the water column, could swim, could access resources that crawlers could never reach. The Cambrian cephalopods were small, their shells measured in centimeters. They were experimenting with a new way of life, testing the possibilities of buoyancy and swimming, not yet dominant, not yet diverse. The Ordovician changed everything. As the GOBE transformed marine ecosystems, cephalopods radiated alongside everything else. New shell shapes evolved: straight cones, curved cones, coiled shells that would eventually give rise to the ammonites of later eras. New sizes became possible as oxygen levels rose and food became more abundant. New ecological roles opened as the tiered communities of the Ordovician created opportunities for predators that could move vertically through the water column. The nautiloids, the great group that includes all these early cephalopods, diversified into hundreds of species. Some remained small, filling niches as mid-level predators or scavengers. Others grew large, very large. The straight-shelled orthocones, including Endoceras and its relatives, became the apex predators of their age. How do you hunt when you are 6 meters long and shaped like a torpedo? The mechanics of orthocone movement remain debated. These were not fast swimmers. Their straight shells created drag. Their bodies were oriented vertically in the water. Their jet propulsion systems were probably weak compared to modern squid. Most researchers believe they were ambush predators, drifting near the seafloor or hovering in the water column, waiting for prey to come within range. The attack would have been sudden. Cephalopods have tentacles, muscular arms lined with suckers or hooks, capable of grasping prey and drawing it toward the mouth. At the center of those tentacles sits a beak, a hard, parrot-like structure made of chitin, capable of biting through shell, through armor, through anything that might struggle in the animal's grip. Endoceras could have seized a trilobite in its tentacles, cracked the calcite exoskeleton with its beak, and consumed the soft tissues within. Direct evidence exists. A trilobite fossil from the late Ordovician of Ontario, a specimen of pseudogigites, bears a bite mark that matches the shape of a cephalopod beak. The trilobite died from the attack. It never molted again, never healed the wound, simply died and was buried with the evidence of its murder preserved in stone. The bite mark matches the size of beaks found in Camaraoceras, a close relative of Endoceras known from the same formation. This is paleontology's equivalent of a crime scene photograph. The predator, the prey, the cause of death, all preserved across 450 million years, waiting for someone to read the evidence. The cephalopods did not rule alone. They shared apex predator status with another group, one even stranger in appearance. The eurypterids, sea scorpions, appeared in the Ordovician fossil record, their bodies armored, their front appendages modified into grasping claws or slashing spines. They were arthropods, relatives of modern horseshoe crabs and arachnids, and some of them grew large. Not as large as the giant orthocones, but large enough to threaten anything on the seafloor, large enough to compete for prey, large enough to matter. Megalograptus was among the Ordovician eurypterids, a predator perhaps a meter long, its foremost limbs armed with spines for capturing prey. It probably hunted on or near the seafloor, pursuing trilobites, worms, smaller arthropods, anything it could catch and subdue. Later eurypterids would grow much larger, reaching 2 meters or more in the Silurian and Devonian, but even the Ordovician forms were formidable. Between the cephalopods above and the eurypterids below, the Ordovician seas had become dangerous. The Cambrian had been a world of small predators, of anomalocaridids and priapulid worms, threats measured in tens of centimeters. The Ordovicians scaled up the danger. Meters of predator now cruised the waters. Armor and spines and enrollment and burrowing, all the defensive innovations of the trilobites, were responses to this new reality. The arms race had begun, the eternal cycle of predator and prey that would drive evolution for the next 500 million years. The Ordovician established the pattern. Everything afterward was variation on the theme. The giant cephalopods were not limited to one lineage. Endoceras was an endocerid, characterized by a distinctive internal structure, cone-shaped deposits within its siphuncle that may have served as counterweights, balancing the shell so the animal could maintain a horizontal posture. Cameroteras belonged to the same group, reaching similar sizes, occupying similar ecological roles. Other nautiloid groups evolved different solutions. The actinocerids developed complex internal structures that may have allowed faster buoyancy adjustment. The tarphyserids coiled their shells, creating more compact, maneuverable forms. The oncochorids shortened their shells dramatically, producing stubby, bullet-shaped animals that may have been faster swimmers than their elongate relatives. The diversity of forms reflected the diversity of niches. The Ordovician seas contained predators specialized for different depths, different prey, different hunting strategies. Some patrolled the open water, others lurked near the bottom. Some may have been active hunters, pursuing prey through the water column. Others were almost certainly ambush predators, conserving energy until opportunity swam within reach. We cannot watch them hunt. We cannot observe their behavior, their social interactions, their reproductive strategies. We have only the shells, beautiful and enigmatic, and the occasional trace of predation, a bite mark here, a damaged shell there, that hints at the violence of their lives. The endocarids reached their peak in the Middle Ordovician and then declined. The pattern is common in paleontology. A group evolves, diversifies, dominates for a time, and then fades, replaced by newer lineages better suited to changing conditions. The endocarids gave way to other nautiloid groups, their giant straight shells becoming less common in the Late Ordovician fossil record. By the end of the period, by the time the mass extinction struck, the true giants were already rare. They did not survive the extinction. The great orthocones, the 6-meter predators, the lords of the Ordovician water column, all of them vanished in the catastrophe that closed the period. Some nautiloids persisted, would continue through the Silurian and beyond, would eventually give rise to the single surviving genus, Nautilus, that still swims in the Pacific today. But the giants were gone. Their brief reign had lasted perhaps 50 million years. In that time, they had transformed the ecology of the oceans, creating predation pressure that drove defensive evolution in every prey species, establishing the pattern of apex predation that would characterize marine ecosystems ever after. Sharks, mosasaurs, plesiosaurs, orcas, all the marine predators that followed owed something to the precedent established by Endocheirus and its kin. The giant cephalopods invented the role of ocean hunter. Everything that followed learned from their example, whether or not it knew the lesson was being taught. In the warm shallows, far from the deep water hunting grounds of the giant orthoconies, the cephalopod radiation continued in smaller forms. Coiled nautiloids were evolving, their shells spiraling into compact packages that sacrificed length for maneuverability. These were the ancestors of the ammonites, the group that would dominate Mesozoic seas, filling the oceans with coiled shells in every conceivable variation. The ammonites would not appear for another 100 million years, but their body plan was being sketched in the Ordovician, tested, refined, prepared for its future success. Small orthocones persisted as well, filling niches as mid-level predators, scavengers, perhaps even filter feeders. The cephalopod body plan was versatile, adaptable, capable of modification for almost any marine lifestyle. What had begun as a snail with a flotation device had become a dynasty, a lineage that would produce everything from giant squid to chambered nautilus, to the octopuses that would eventually be recognized as among the most intelligent invertebrates on Earth. The Ordovician cephalopods were pioneers. They were exploring possibilities that their descendants would elaborate for 500 million years. They were inventing predation at scale, demonstrating what a mobile, intelligent, tentacled hunter could achieve in an ocean full of prey. The tentacled giants are gone now, their shells compressed into limestone, their soft bodies decayed beyond any hope of preservation. What remains is inference, reconstruction, the patient work of paleontologists who study shell geometry and growth lines and stable isotopes, trying to understand how these animals lived. The picture that emerges is incomplete, tantalizing, a sketch rather than a portrait. The giants once swam here. Their shadows fell across seafloors where trilobites hunted and brachiopods filtered and crinoids swayed in ancient currents. 6 meters of shell, pointed like a spear, moving through warm Ordovician water. The trilobites and cephalopods filled the seas with motion, with hunting, with the ancient drama of predator and prey. Below them, anchored to the seafloor, a different kind of life was flourishing. Organisms that did not hunt, did not chase, did not kill. Filter feeders, reef builders, the patient architects of a tiered world. They had transformed the ocean floor into something the Cambrian would not have recognized. They built upward. In the Cambrian, life had hugged the seafloor. Organisms crawled across sediment, burrowed into mud, grazed on bacterial mats that coated every surface. The water column above was largely empty, a 3-dimensional space that almost nothing had learned to exploit. Food particles drifted past uncaptured. Currents carried nutrients that no one harvested. The ocean was a house with only the ground floor occupied. The Ordovician added stories to that house. Floors rose above floors, life stacked upon life. The flat, 2-dimensional communities of the Cambrian gave way to tiered ecosystems where organisms occupied distinct levels, each filtering different water masses, each accessing different resources. At the base, brachiopods carpeted the sea floor. These bivalved animals, superficially similar to clams but unrelated, had existed since the Cambrian, but the Ordovician saw their great radiation. Hundreds of genera evolved, adapted to every conceivable substrate and depth and water chemistry. Some attached themselves to rocks with fleshy stalks called pedicles. Others lay free on the sediment, their weight holding them in place. Still others cemented themselves directly to hard surfaces, immobile, permanent, drawing water through their shells and extracting food particles with delicate filtering structures called lopophores. The brachiopod carpet was dense. In some Ordovician deposits, their shells are packed so tightly that you cannot see the sediment between them. Each animal was small, a few centimeters across, but together they formed living pavement, a biological substrate that other organisms could colonize. Above the brachiopods rose the bryozoans. Bryozoans were new. The first definitive bryozoan fossils appear in the early Ordovician, making them the last major animal phylum to enter the fossil record. They were colonial organisms, each individual animal, called a zooid, measuring less than a millimeter, but the colonies they built could span meters. The zooids secreted calcium carbonate skeletons, constructing branching, encrusting, or lacy structures that rose above the seafloor like miniature trees. Each zooid filtered water with a ring of tentacles, capturing bacteria and organic particles, passing nutrients to its neighbors through shared tissue connections. The colonial strategy was powerful. A single zooid was insignificant, vulnerable, incapable of affecting its environment. A colony of thousands was an ecosystem engineer, creating three-dimensional structure where none had existed, providing habitat for countless other organisms, changing water flow patterns across the seafloor. Bryozoan colonies grew in forms that seem almost architectural. Some were delicate and lacy, thin sheets of calcite perforated by thousands of tiny holes, each hole the home of a zooid. Others were robust and branching, their skeletons thick enough to resist wave action, strong enough to persist for years or decades. Still others encrusted hard surfaces, shells, rocks, the stems of crinoids, spreading across any available substrate like living paint. The variety was staggering. Modern bryozoans include perhaps 6,000 species. The Ordovician radiation established the group's fundamental diversity, experimenting with colonial forms that would persist for the next 500 million years. Higher still rose the crinoids. Crinoids are echinoderms, relatives of starfish and sea urchins, but they look nothing like their crawling cousins. A typical crinoid consists of a stem, a flexible column of stacked calcite discs, anchored to the seafloor at one end and crowned at the other by a cup-shaped body surrounded by feathery arms. The arms are lined with tube feet that capture food particles from the water, passing them down grooves toward the central mouth. The effect is flower-like. Victorian naturalists called them sea lilies, and the name has stuck, though crinoids are animals, not plants, and their graceful forms are feeding structures, not petals. A crinoid meadow sways in the current like a field of flowers in the wind, each animal waving its arms, each arm combing the water for food. Ordovician crinoids could grow tall. Some species reached heights of a meter or more, their stems lifting their feeding crowns high above the seafloor into water masses that the brachiopods and bryozoans below could not reach. They were tearing specialists, occupying the upper levels of the benthic community, filtering water that had not yet been depleted by the organisms beneath them. The stems were their vulnerability. A crinoid anchored to the bottom was immobile, unable to flee predators, unable to relocate when conditions changed. If a cephalopod or eurypterid attacked, the crinoid could only retract its arms and hope its calcite skeleton provided sufficient protection. Many did not survive such encounters. Crinoid stems litter Ordovician seafloors, the scattered remains of animals torn from their moorings, their cups and arms broken and dispersed. Yet they persisted. The strategy worked well enough, often enough, that crinoids became a defining feature of Paleozoic marine communities. Their fossils are among the most common in Ordovician limestones, their disc-shaped stem segments accumulating in such abundance that some rock layers are composed almost entirely of crinoid debris. The tearing was not merely physical, it was ecological, a division of resources that allowed more species to coexist than a flat community could support. Consider a patch of Ordovician seafloor. The brachiopods filter water at the sediment surface, capturing particles that have drifted down from above. The bryozoans, growing a few centimeters higher, filter water that the brachiopods cannot reach. The crinoids, rising higher still, access currents that pass over the bryozoan colonies untouched. Each tier exploits a different slice of the water column, a different portion of the available food supply. This is niche partitioning, the ecological mechanism that allows competitors to coexist. If all these animals filtered the same water, they would compete directly, and the most efficient filter feeder would exclude the others. By dividing the water column into vertical zones, they reduce competition, allowing greater diversity than a single-tier community could sustain. The Ordovician invented this system. The tiered suspension feeding communities that would dominate marine ecosystems for the next 250 million years through the Silurian, the Devonian, the Carboniferous, the Permian were established in the Ordovician. The ecological structure was set. Everything afterward was elaboration. Paleontologist Jack Sepkoski, who spent his career analyzing diversity patterns in the fossil record, called this the Paleozoic evolutionary fauna. It was distinct from the earlier Cambrian fauna, with its trilobite-dominated deposit-feeding communities. It was distinct from the later modern fauna, with its bivalve and gastropod diversification. The Paleozoic fauna was the Ordovician's gift to subsequent ages, a template for how marine ecosystems could be organized. Reefs rose from the tiered seafloors. The word requires careful definition. Modern coral reefs are built primarily by scleractinian corals, animals that would not evolve until the Triassic, 200 million years after the Ordovician ended. Ordovician reefs were different, constructed by different organisms using different architectural strategies, achieving different scales and complexities. The builders were varied. Tabulate corals contributed their colonial skeletons, each corallite a tiny tube, thousands packed together into mound-shaped or branching structures. Rugose corals added solitary or colonial forms, their internal structures distinct from the tabulates. Stromatoporoids, enigmatic organisms whose precise affinities remain debated, built massive calcareous skeletons that could form the cores of reef structures. Bryozoans contributed their lacy frameworks. Sponges added their siliceous or calcareous bodies. The result was a consortium, multiple groups cooperating, sometimes competing, to build three-dimensional structures that rose above the surrounding seafloor. These reefs were smaller than modern coral reefs. They did not form the vast barrier systems that stretch for thousands of kilometers along modern tropical coastlines. Ordovician reefs were typically patch reefs, isolated mounds rising from the seafloor, rarely more than a few meters high, rarely spanning more than a few hundred meters across. Yet they were ecologically significant. A reef creates habitat. Its three-dimensional structure provides shelter for fish, for crustaceans, for mollusks, for countless organisms that cannot construct their own refuges. Its surfaces offer substrate for encrusting organisms, for boring organisms, for anything that needs a hard surface in a world of soft sediment. The Ordovician reefs were islands of complexity in seas that were otherwise more uniform, hotspots of diversity where species accumulated. The filter feeders transformed more than the water column. They transformed the sediment beneath them. A brachiopod draws water into its shell, extracts food particles, and expels waste. That waste settles to the seafloor, organic material packaged into pellets that become food for deposit feeders below. A crinoid does the same at greater height, raining organic debris onto the community beneath it. The filter feeders were not just feeding themselves, they were feeding the seafloor, converting suspended particles into benthic resources. This process, called biodeposition, changed the nature of marine sediments. Cambrian seafloors had accumulated organic matter slowly, dependent on particles drifting down from the water column at whatever rate physics dictated. Ordovician seafloors received an accelerated rain of organic material, processed and packaged by the filter feeders above. The benthos became richer, supporting more deposit feeders, more burrowers, more organisms that depended on organic matter in the sediment. The feedback loops multiplied. More filter feeders meant more biodeposition. More biodeposition meant more resources for deposit feeders. More deposit feeders meant more bioturbation, the churning and mixing of sediment by burrowing organisms, which released nutrients, which supported more plankton, which fed more filter feeders. The Ordovician ecosystem was a machine that amplified its own productivity, each component enhancing the others. You can see the remains of this tiered world in museum collections around the globe. The limestone slabs bristle with life. Brachiopod shells cluster in dense pavements. Bryozoan colonies branch and spread across the rock surface. Crinoid stems lie scattered like fallen columns, their cup-shaped heads occasionally preserved, their arms spread wide in death as they once spread in life. Tabulate coral colonies form dark masses, their tiny corallites visible as honeycomb patterns on weathered surfaces. These are snapshots of communities, frozen in stone, preserved by the same calm sedimentation that allowed such diversity to flourish. The animals died, were buried, were compressed and lithified, and now they sit in glass cases, labelled with Latin names, waiting for someone to look at them and wonder what the living community might have resembled. The wondering requires effort. A fossil slab is not an ecosystem. It is a jumble of shells, a confusion of fragments, a puzzle with most of the pieces missing. The soft-bodied organisms are gone entirely, leaving no trace. The spatial relationships are distorted by compaction and dissolution. The time dimension is collapsed. Animals that lived years or centuries apart are pressed together into a single layer, their temporal separation invisible. Paleontologists spend careers learning to read these slabs, to extract ecological information from taphonomic chaos. They measure shell orientations to infer current directions. They analyze size distributions to understand population dynamics. They study the boring and encrusting organisms that colonized shells after death, reconstructing the post-mortem history of the community. Each slab is a text in an ancient language, and fluency comes slowly. The tiered world left its signature in stone. Brachiopods below, bryozoans above, crinoids reaching toward the surface, the whole structure organized by competition and cooperation and the physics of water flow. The Ordovician filter feeders had rewritten the rules of marine community organization. The hunters and the hunted moved through their forests, their meadows, their patient architectures. Somewhere beneath this living scaffold, pressed against the seafloor, something else was stirring, a different kind of existence entirely, one that had been developing in the darkness of Ordovician seas since the period began. The first vertebrates. The armor came first. The jaws came later. 500 million years ago, in the shallow seas of the Cambrian, something unprecedented appeared in the fossil record. A small, soft-bodied creature with a stiffening rod running the length of its body. A notochord, the defining feature of our phylum. Picaia, from the Burgess Shale, was not a fish. It had no bones, no scales, no fins worthy of the name. It was a wriggling ribbon of tissue, perhaps 5 centimeters long, swimming with undulations of its body through waters that would one day become the Canadian Rockies. Picaia was a beginning. The vertebrate story would unfold from ancestors like it, from soft-bodied chordates that left almost no fossil record, from creatures so fragile that their preservation required exceptional circumstances. The Cambrian chordates were rare, small, insignificant, background players in a world dominated by arthropods. The Ordovician changed their prospects. Somewhere in the early part of the period, some lineage of chordate evolved a new trick. It began depositing minerals in its tissues, building hard structures from calcium phosphate, the same material that would eventually form your teeth, your bones, the skeleton that holds you upright. The first vertebrate hard parts were not internal skeletons. They were external armor, bony plates covering the head and front of the body, protection against a world that was becoming increasingly dangerous. The armored fish had arrived. Paleontologists call them ostracoderms, shell-skinned, though the term is informal, grouping together several distinct lineages that independently evolved similar solutions to similar problems. They were jawless, all of them, their mouths simple openings suited for filter feeding or sucking organic material from sediment. They were small, most of them, measured in centimeters rather than meters. They were sluggish, probably their heavy armor limiting speed and maneuverability. They were also the ancestors of everything with a backbone that would ever live. Arandaspis prionotolepis swam in the shallow seas that covered Central Australia 480 million years ago. The fossils come from the stairway sandstone of the Northern Territory, rocks deposited in a marine environment when Australia was part of Gondwana, positioned in tropical latitudes, its coastlines washed by warm Ordovician waters. Arandaspis was discovered in 1959 and formally described in 1977, one of the earliest ostracoderms known from relatively complete material. The animal was perhaps 15 centimeters long. Its head was encased in a bony shield, the plates ornamented with ridges and tubercles, the eyes positioned on the sides for a wide field of view. Behind the head shield, the body was covered with smaller scales, each scale a tiny plate of bone, the whole arrangement providing protection while allowing flexibility for swimming. The tail was probably the main propulsive organ, beating side to side in the manner of modern fish. Arandaspis had no jaws. Its mouth was a simple slit at the front of the head, probably fringed with soft tissue, probably used to suck water and filter out organic particles. It was not a predator. It could not bite, could not tear, could not pursue prey with aggressive intent. It was a grazer, a filter feeder, an animal that made its living on the small and the slow. This seems humble. It was revolutionary. Arandaspis and its relatives were the first vertebrates to leave a significant fossil record, the first members of our lineage to have bodies robust enough to preserve across geological time. They were pioneers, experimenting with a body plan that would eventually produce sharks and salmon, frogs and falcons, dinosaurs and dolphins, and one peculiar lineage of African apes that would learn to wonder about its own origins. The armor was a response to predation. The Ordovician seas were dangerous. Cephalopods cruised the water column with tentacles and beaks. Eurypterids stalked the seafloor with grasping claws. Large predatory arthropods, anomalocaridids surviving from the Cambrian or their Ordovician descendants, may have posed additional threats. A soft-bodied chordate swimming slowly through these waters would have been easy prey. Something had to change. Bone changed everything. A layer of hard tissue between predator and prey, a shield that beaks could not easily penetrate, armor that claws might scrape without finding purchase. The cost was significant. Bone is heavy, metabolically expensive to produce and maintain, a burden that limits speed and agility. The benefit was survival. The armored fish lived long enough to reproduce. The unarmored did not. The pattern is familiar from later evolutionary history. Turtles evolved shells. Armadillos evolved bony plates. Pangolins evolved scales of keratin. When predation pressure intensifies, armor is a common response, a trade-off of mobility for protection that works well enough in the right circumstances. The ostracoderms found their circumstances. They diversified through the Ordovician, spreading across the shallow seas of multiple continents. Sacabambaspis from Bolivia, shows that they reached the margins of Gondwana. Astraspis from North America demonstrates their presence on Laurentia. By the late Ordovician, jawless armored fish were a modest but established component of marine faunas worldwide. The fossils are rare. The importance is not. Vertebrate paleontology suffers from a preservation bias. Bones fossilize well, but only if they are buried quickly in the right conditions, only if the sediment chemistry favors preservation, only if subsequent geological processes do not destroy what was preserved. Soft tissues almost never fossilize. Cartilage fossilizes poorly. Even bone can dissolve if groundwater is acidic enough, can be crushed if burial pressure is too great, can be eroded away if rocks are exposed to weathering before anyone finds them. The Ordovician vertebrate record is therefore fragmentary. Isolated scales, partial head shields, occasional articulated specimens from exceptional localities. Paleontologists work with what they have, reconstructing animals from pieces, inferring anatomy from fragments, building a picture of early vertebrate evolution from evidence that would barely fill a museum display case. What that evidence shows is a radiation. Multiple lineages of jawless fish evolved independently, developing different arrangements of armor, different body shapes, different ecological strategies. The heterostracans had solid head shields covering the entire front of the body. The anaspids had smaller, more flexible arrangements of plates. The thelodonts were covered entirely in tiny scales, their bodies more streamlined, their lifestyles perhaps more active. None of these groups survived to the present day. All of them contributed to our understanding of how vertebrates evolved, how the body plan was modified and refined, how the lineage that would produce jawed fish, and eventually us, emerged from jawless ancestors. The mouth without jaws seems limiting. It was also ancestral. Your jaw evolved from gill arches. The bony or cartilaginous supports that hold open the gills of fish were modified over millions of years into structures that could bite. The first gill arch became the jaw itself. The second became the hyoid apparatus that supports your tongue. The transformation happened after the Ordovician in the Silurian or Devonian, producing the gnathostoms, the jawed vertebrates, that would come to dominate both aquatic and terrestrial environments. The ostracoderms were pre-jawed. They represent the ancestral condition, the state of vertebrate anatomy before that transformation occurred. Studying them is studying our own deep history, examining the body plan from which our body plan was derived. The jawless condition is not primitive in any pejorative sense. Lampreys and hagfish, the only jawless vertebrates surviving today, are highly specialized, successful in their own niches, capable of feats that jawed fish cannot match. A lamprey can attach to a host fish with its sucker mouth, rasp through scales and skin, feed on blood and body fluids for weeks. A hagfish can tie its body in knots to gain leverage, can secrete slime in quantities that deter predators, can survive for months without food. These are not failed evolutionary experiments, they are alternative solutions, paths not taken by the majority of vertebrates but successful nonetheless. The Ordovician ostracoderms were exploring possibilities. Some of those possibilities would be abandoned, others would be modified into something new. The vertebrate body plan was plastic, changeable, responsive to selection pressures that we can only partially reconstruct from the fossil record. The transition to land was unimaginably far in the future. The first vertebrate footprints on terrestrial sediment would not appear for another 60 million years in the late Devonian. The first fully terrestrial vertebrates, amphibians capable of spending their entire lives on land, would take longer still. The Ordovician ostracoderms were purely aquatic, their bodies adapted for swimming, their physiology dependent on water for respiration, for reproduction, for every aspect of existence. Yet the potential was there. The vertebrate body plan contained possibilities that the Ordovician fish could not have anticipated. Lungs would evolve from swim bladders, limbs would evolve from fins. The bony armor that protected Arandaspis from Ordovician predators would be internalized, transformed into the endoskeleton that supports your body from within. Evolution does not plan ahead. It cannot see the future, cannot anticipate what adaptations might be useful in environments that do not yet exist. The ostracoderms evolved armor because armor was useful in the Ordovician. They could not know that their descendants would walk on land, would fly through air, would eventually build machines that could leave the planet entirely. The vertebrate story is a story of transformation. Each generation is adapted to its present circumstances, unaware that it is also a transitional form, a link between what came before and what will come after. The ostracoderms were our ancestors, swimming in warm Ordovician seas, armored against dangers they could perceive, carrying within their bodies the seeds of futures they could not conceive. The first backbones were simple, notochords stiffened with cartilage, mineral deposits concentrated in external armor rather than internal skeleton. The architecture would grow more complex in later periods, vertebrae segmenting the spinal column, ribs protecting internal organs, limb bones articulating in ways that allowed new modes of locomotion. The Ordovician vertebrates were rough drafts, first attempts, sketches that later evolution would revise and elaborate. They swam through forests of crinoids, past meadows of brachiopods, beneath the shadows of giant cephalopods. They filtered organic particles from water that had already been filtered by bryozoans and corals. They were small players in a large ecosystem, insignificant by the standards of their time, overshadowed by trilobites and nautiloids and the spectacular diversity of invertebrate life. Their insignificance was temporary. Their lineage would outlast the trilobites, outlast the giant cephalopods, outlast most of the organisms that dominated Ordovician seas. The vertebrates were patient. They had time. While the armored fish probed the sediment for food, while the filter feeders built their tiered communities, while the predators hunted and the prey fled, something else was happening. Far from the crowded seafloors, beyond the reach of cephalopod tentacles and eurypterid claws, life was attempting something unprecedented. The first organisms were crawling onto land. Not everything swam, not everything crawled. Some organisms simply floated. The Ordovician oceans teemed with plankton, organisms too small or too weak to swim against currents, drifting wherever the water carried them. Some were single-celled, invisible to the naked eye, forming the base of food webs that supported everything above. Others were larger, colonial, their bodies designed for flotation rather than locomotion, their lives spent riding the currents of a world-spanning sea. Among the drifters, none left a more distinctive fossil record than the graptolites. Graptolites were colonial animals, each colony consisting of dozens or hundreds of tiny individuals, zooids, housed in cup-shaped structures arranged along one or more branches. The branches were made of collagen, a protein that normally decays rapidly after death. Yet graptolites fossilize beautifully, their delicate structures preserved as carbon films on black shales, thin, dark lines that look like pencil marks scratched across the rock. The name reflects this appearance. Graptolite derives from the Greek graptos, meaning written, and lithos, meaning stone. 19th century naturalists who first studied these fossils thought they resembled ancient inscriptions, messages left by some unknown hand on the surfaces of rocks pulled from Welsh hillsides and Scandinavian quarries. The messages were biological, not linguistic. Each mark was a colony, each colony a community of interconnected animals, each animal a filter feeder drawing food from Ordovician waters. The colonies took many forms. Some graptolites were bushy, their branches radiating outward from a central point like the fronds of a fern. These benthic forms attached themselves to the seafloor, living much as bryozoans did, filtering water from a fixed position. They were the ancestral condition, the starting point from which more specialized forms evolved. The planktonic graptolites broke free. Sometime in the late Cambrian or earliest Ordovician, certain graptolite lineages abandoned the seafloor and took to the open water. Their colonies developed flotation structures, gas-filled bulbs called pneumatosacs, or frothy tissue masses called nemas, that kept them suspended in the water column. They drifted with currents, fed on whatever organic particles the water delivered, reproduced and died far from any solid surface. The transition was spectacularly successful. Planktonic graptolites diversified through the Ordovician, evolving colony architectures that seem almost engineered. Some had branches that spiraled around a central axis, corkscrew shapes spinning slowly as they drifted. Others had branches arranged in rows, neat parallel lines like the teeth of a comb. Still others reduced their colonies to just one or two branches, streamlined forms that minimized drag. Didymagraptus was among the most distinctive. Its colonies consisted of two branches hanging downward from a flotation structure, the whole arrangement resembling a tuning fork suspended in the water. Millions of Didymagraptus colonies drifted through Ordovician seas, their forked shapes appearing in rocks from every continent, a global signature of early and middle Ordovician time. Graptolites became the timekeepers of the Ordovician. Evolution was rapid in these drifting colonies. New species appeared frequently, spread quickly across the world's oceans, and went extinct after relatively brief spans of geological time. A graptolite species might persist for only a few million years, sometimes less, before being replaced by descendants with modified colony structures. This rapid turnover made graptolites extraordinarily useful for dating rocks. Charles Lapworth, the same geologist who defined the Ordovician period, pioneered the use of graptolites for biostratigraphy. Working in the southern uplands of Scotland during the 1870s and 1880s, Lapworth collected graptolites systematically, noting which species occurred in which rock layers, building a sequence that could be applied to rocks elsewhere. If you found a particular graptolite species in Scotland and the same species in Wales, you could conclude that those rocks were approximately the same age, deposited during the same interval of geological time. The method revolutionized stratigraphy. Before Lapworth, correlating rocks between regions was difficult, dependent on matching rock types or tracing physical layers across the landscape. After Lapworth, fossils became the primary tool for geological correlation. Graptolites were especially valuable because their planktonic lifestyle had dispersed them globally. The same species drifted on currents from Laurentia to Baltica to Gondwana, leaving identical fossils in rocks deposited on opposite sides of vanished oceans. Modern geologists still use graptolites. The Ordovician period is divided into stages, each stage defined by the first appearance of particular graptolite species. When you read that a fossil comes from the Darwinian stage, you are reading a graptolite-based determination, a date anchored by the evolutionary history of drifting colonial animals that have been dead for 460 million years. The graptolites were not alone in the plankton. Acritarchs, tiny organic walled cysts of uncertain biological affinity, had dominated the phytoplankton since the Proterozoic. They were probably the resting stages of various algae, protective capsules that allowed single-celled organisms to survive unfavorable conditions. Acritarchs diversified through the Ordovician, their ornamented walls becoming more elaborate, their assemblages becoming more diverse, tracking environmental changes that affected the surface waters of ancient seas. Chitinozoans appeared in the Ordovician flask-shaped organic structures that may have been the eggs of unknown marine animals. Their function remains debated. Their stratigraphic utility is established. Like graptolites, chitinozoans evolved rapidly enough to serve as biostratigraphic markers, their changing forms recording the passage of Ordovician time. Radiolarians built skeletons of silica, intricate geometric frameworks that sank to the seafloor when the organisms died, accumulating in sediments that would eventually become chert. The Ordovicians saw radiolarian diversification, the elaboration of skeletal architectures that would continue evolving for the next 500 million years. The planktonic ecosystem was layered, phytoplankton at the surface capturing sunlight, converting carbon dioxide and water into organic matter through photosynthesis. Zooplankton above and below, feeding on the phytoplankton or on each other, transferring energy up the food chain. Larger drifters like graptolites filtering particles from the water, adding another trophic level to the system. The whole community suspended in the water column, rising and falling with daily rhythms, drifting with currents that circled the globe. The conodonts swam through this drifting world. For over a century, conodonts were among the most mysterious fossils known. They appeared as tiny, tooth-like structures, cones, bars, blades, and platforms of calcium phosphate, extracted by the thousands from dissolved limestone samples. Paleontologists used them for biostratigraphy, recognizing their value for dating rocks, classifying them into species and genera, building evolutionary sequences. Yet no one knew what kind of organism had produced them. The mystery deepened with each new discovery. Conodont elements were clearly biological, clearly produced by some living thing, clearly arranged in complex apparatuses of multiple elements working together. They showed wear patterns, suggesting they functioned in feeding. They occurred in rocks spanning 300 million years, from the Cambrian to the Triassic, found on every continent, in every marine environment. Whatever made them was successful, widespread, enduring. The answer came in 1983. That year, researchers studying Carboniferous rocks from Scotland found something unprecedented, a complete conodont animal, soft tissues preserved alongside the familiar phosphatic elements. The creature was eel-like, perhaps 4 centimeters long, with large eyes, a notochord, V-shaped muscle blocks, and a tail fin. The conodont elements sat in its head, arranged as a feeding apparatus used to grasp and process food. Conodonts were vertebrates, or very nearly so. Their precise position on the vertebrate family tree remains debated, but they were clearly chordates, clearly closer to us than to any invertebrate group. The tooth-like elements were not teeth, but something analogous, independently evolved structures that served similar functions. The Ordovician conodonts were among the earliest and most diverse members of the group. They swam through planktonic clouds, their phosphatic apparatuses seizing prey, their eel-like bodies undulating through waters that also held the first armored fish. 2 lineages of early vertebrates sharing the Ordovician seas, one destined for extinction in the Triassic, one destined to inherit the Earth. You can hold Ordovician plankton in your hand. Black shales from Wales, from Scandinavia, from the Appalachians, from the margins of ancient Gondwana. Split them along bedding plains and graptolites appear, silver-grey on black, their branching structures preserved with remarkable fidelity. The smallest details are visible. Individual cups where zooids once lived, the connecting stolons that linked colony members, the attachment structures that anchored some forms to floating debris. These are not rare fossils. Graptolite-bearing shales are abundant enough that you can purchase specimens for modest sums, common enough that geology students routinely collect them on field trips, numerous enough that museums display them by the hundreds. The organisms that seemed so delicate, so ephemeral, so dependent on the vagaries of current and wind, left a fossil record of striking persistence. The persistence resulted from their lifestyle. Planktonic organisms that die in the open ocean sink. If they sink through oxygenated water, scavengers consume them. Bacteria decompose them. Nothing reaches the seafloor intact. If they sink through anoxic water, oxygen-depleted zones where decomposition is slowed, they may reach the bottom relatively intact, may be buried in fine-grained sediment, may be preserved as carbon films in shales that will someday be exposed on Welsh hillsides. The Ordovician had extensive anoxic zones. The greenhouse climate, the stratified oceans, the arrangement of continents that restricted water circulation, all contributed to oxygen depletion in deep waters, creating conditions ideal for graptolite preservation. The black shales that Lapworth studied, that defined the Ordovician's subdivisions, that still serve as reference sections today, are monuments to anoxia, records of seas where oxygen was scarce and preservation was exceptional. The drifters traced patterns invisible to creatures bound to the seafloor. Ocean currents in the Ordovician followed paths dictated by continental positions, wind patterns, and the rotation of the Earth. The Iapetus Ocean, separating Laurentia from Baltica and Gondwana, had its own circulation systems. Equatorial currents flowed westward, deflected by continental margins, forming gyres that circled endlessly. Graptolite colonies rode these currents, some species restricted to particular water masses, others cosmopolitan, found wherever ocean waters connected. The biogeography of planktonic organisms reveals ancient circulation patterns. When graptolite species are restricted to certain regions, they indicate barriers, currents that did not connect, water masses that remained isolated. When species are widespread, they indicate connectivity, circulation systems that carried drifting organisms across ocean basins, distributing them to distant shores. Paleontologists read these distribution patterns like texts, extracting information about Ordovician oceanography from the fossils of animals that simply went where the water took them. The graptolites did not know they were mapping currents. They were just living, feeding, reproducing, dying, their bodies sinking through oxygen-poor waters to accumulate in sediments that would preserve them for hundreds of millions of years. The drifters were witnesses to an ocean in motion, a world of currents and gyres, warm surface waters and cold depths, oxygen-rich zones and anoxic basins. Their fossils record that motion, frozen into stone, waiting for someone to read what the currents wrote. While the plankton drifted and the graptolites fed, and the conodonts hunted through clouds of organic particles, change was coming from an unexpected direction. The sea had grown crowded, tiered, complex. Life had filled nearly every available marine niche. The next great transformation would require a new arena entirely. Something was moving toward the shore, toward the barren rocks and empty air of a world that had never known life. The rocks were bare, the air was empty. For 4 billion years, the continents had been deserts of stone. No roots split the bedrock, no leaves captured the sunlight, no soil softened the transition between rock and atmosphere. Only naked mineral surfaces, scoured by wind, cracked by frost, washed by rain that carried nothing organic back to the sea. The land was sterile in a way that modern humans cannot easily comprehend. Every mountainside you have ever seen has been clothed in life. Every valley you have walked through has been shaped by roots and stabilized by vegetation. The Ordovician continents had none of this. They were planets unto themselves, worlds as barren as Mars. The oceans had been alive for 3 billion years. Life had evolved complexity, diversity, ecosystems of staggering intricacy. Trilobites had developed crystal eyes. Cephalopods had grown to 6 meters. Filter feeders had built tiered communities that processed the water column with industrial efficiency. The seas were crowded, competitive, dangerous. The land was empty. It waited. The invasion began with green algae, Chlorophyte algae had thrived in shallow marine and freshwater environments since the Proterozoic. They were photosynthesizers, capturing sunlight with the same chlorophyll molecules that would eventually color every forest and meadow on Earth. Some lineages had adapted to the intertidal zone, tolerating periodic exposure to air as tides ebbed and flowed. Others had colonized freshwater streams and ponds, environments where conditions were harsher than the stable ocean, where temperature fluctuated and water chemistry varied, and desiccation was a constant threat. These marginal environments were training grounds. The algae that survived in tide pools and ephemeral ponds had already evolved partial solutions to the challenges of terrestrial life. They could tolerate some drying. They could survive temperature swings. They had the biochemical foundations upon which true land plants would be built. The transition from aquatic alga to terrestrial plant required solving several problems simultaneously. Water loss was paramount. Air is desiccating, and a cell that cannot retain moisture will die within hours of exposure. Gas exchange was equally critical. Photosynthesis requires carbon dioxide from the atmosphere, but any opening that admits carbon dioxide also allows water vapor to escape. Structural support posed another challenge. Water-buoys organisms and an alga that grows upright in a pond will collapse under its own weight in air. The solutions evolved piecemeal over millions of years in lineages that left almost no fossil record. Waxy cuticles developed, coating plant surfaces with water-resistant compounds. Stomata appeared, pores that could open to admit carbon dioxide and close to retain moisture. Rigid cell walls provided support, lignin eventually adding strength that allowed vertical growth. Each innovation was a small step. Together, they constituted a revolution. The oldest evidence of land plants comes from the Middle Ordovician, approximately 470 million years ago. The evidence is not leaves or stems or roots. The earliest land plants were too small, too fragile, too poorly constructed for their vegetative parts to survive in the fossil record. What survives are spores. Spores are reproductive cells, packages of genetic material encased in tough outer walls that protect them from desiccation and decay. Plants release spores into the environment. The spores disperse by wind or water. Under favorable conditions, they germinate, producing new plants. The spore wall is made of sporopollenin, one of the most chemically resistant biological compounds known. Sporopollenin survives conditions that destroy almost everything else: heat, pressure, oxidation, microbial attack. Spores persist when the plants that made them have rotted to nothing. Ordovician sediments contain spores. Specifically, they contain cryptospores, spores with morphologies distinct from anything produced by algae, morphologies that indicate they came from plants adapted to life on land. These cryptospores appear in the fossil record around 470 million years ago, first in Gondwanan rocks from regions that are now Saudi Arabia and Libya and Czech Republic, later spreading to other continents as land plants diversified and dispersed. The plants that made these spores were probably similar to modern liverworts, flat, low-growing organisms that hugged moist surfaces, lacking true roots, lacking vascular tissue, depending on direct contact with water for reproduction. They were not impressive by the standards of later vegetation. A liverwort does not tower, it does not shade, it does not create forest ecosystems or generate oxygen on a planetary scale. A liverwort clings to damp rock and does the minimum necessary to survive. The minimum was enough. From such modest beginnings, all terrestrial vegetation would eventually descend. Jane Gray and William Shear transformed our understanding of early land life. In a series of papers published during the 1980s and 1990s, Gray, a palynologist specializing in fossil spores, and Shear, a zoologist studying early terrestrial arthropods, argued that the colonization of land began far earlier than previously thought. The conventional view had placed land plants in the Silurian, terrestrial ecosystems in the Devonian. Gray and Shear pushed the dates back, presenting evidence from cryptospores and trace fossils that land was colonized during the Ordovician. Their work was initially controversial. The evidence was indirect. Spores without plants, traces without animals, inferences rather than body fossils. Critics argued that cryptospores might have come from aquatic organisms, that trace fossils might have been made by organisms that never truly left the water. The debate continued for years, each new discovery adding weight to one interpretation or another. The weight has shifted toward early colonization. Molecular clock analyses, which estimate divergence times from genetic differences between living organisms, consistently suggest that land plants evolved in the Middle Ordovician or earlier. New cryptospore discoveries continue to push back the earliest evidence. The consensus, never absolute in science, now favors an Ordovician origin for terrestrial vegetation. The plants did not colonize alone. Fungi came with them, or perhaps preceded them. The relationship between plants and fungi is ancient, possibly as old as land plants themselves, possibly older. Modern plants form partnerships with mycorrhizal fungi, their roots intertwined with fungal filaments that extend the root system's reach, accessing nutrients that roots alone cannot obtain. The fungus receives sugars from the plant receives phosphorus and other minerals from the fungus. The partnership is so fundamental that most land plants cannot survive without it. Fossil evidence for early fungi is sparse, their soft bodies rarely preserved. Chemical evidence is more robust. Certain compounds produced only by fungi appear in Ordovician sediments, suggesting that fungal communities were established on land by the Middle Ordovician. Some researchers argue that fungi colonized land before plants, preparing the substrate, beginning the slow process of soil formation that would eventually allow more complex vegetation to establish. The interaction between plants, fungi, and rock was transformative. Roots and fungal hyphae penetrate rock surfaces, secreting acids that dissolve minerals, creating channels that water and air can enter. When organisms die, their organic matter accumulates, mixing with mineral fragments to form soil. Soil retains water, stores nutrients, provides anchorage for larger plants. The process is slow. It takes thousands of years to form significant soil layers, but it is relentless. Once begun, the transformation of bare rock into living landscape cannot be stopped. The Ordovician plants and fungi initiated that transformation. They were pioneers, the first organisms to look at barren continental surfaces and find opportunity rather than obstacle. The atmosphere felt the change. Plants photosynthesize, converting carbon dioxide and water into sugars and oxygen. The oxygen escapes into the atmosphere. The carbon is stored in plant tissue, removed from the atmospheric reservoir for as long as the plant lives, potentially buried in sediments when the plant dies. Plants are carbon pumps, drawing greenhouse gases from the air and replacing them with oxygen. The Ordovician atmosphere contained perhaps 15 times as much carbon dioxide as the modern atmosphere. The greenhouse effect was intense, global temperatures elevated, ice absent from the poles. The first land plants were too sparse, too small, too limited in extent to significantly alter this atmospheric composition. Their effect was local, a slight increase in oxygen near the ground, a slight decrease in carbon dioxide in the immediate vicinity of photosynthesizing tissue. Later plants would change everything. The spread of forests in the Devonian would draw down atmospheric carbon dioxide dramatically, possibly triggering ice ages, certainly transforming global climate. The Carboniferous would see carbon burial on a massive scale, creating the coal deposits that humans would eventually extract and burn, returning ancient carbon to the atmosphere. The coevolution of plants and atmosphere is one of Earth's great feedback systems, each influencing the other over hundreds of millions of years. The Ordovician plants were the beginning of that story. They could not know that their descendants would reshape the planet's climate, would build forests that stretched from pole to pole, would generate the oxygen that animals would breathe. They knew only the immediate challenges: finding water, capturing light, surviving on rocks that offered no welcome. You can find Ordovician plant fossils if you know where to look. The cryptospores are extracted from sediments by dissolving rock samples in acid, washing away the mineral matrix, concentrating the organic residue that remains. The spores are tiny, measured in micrometers, requiring microscopes to see. They are not glamorous fossils. They do not fill museum halls or grace coffee table books. A vial of organic residue, brown and granular, does not inspire the wonder that a complete trilobite or a giant cephalopod shell inspires. Yet those vials contain evidence of one of the most important transitions in the history of life. The movement from water to land transformed the planet more profoundly than any other biological innovation. The photosynthesis that happens on land today dwarfs marine photosynthesis. The carbon stored in terrestrial vegetation and soils exceeds marine carbon storage by orders of magnitude. The weathering acceleration caused by plant roots has altered the chemical cycling of every element on Earth. All of it began with cryptospores in Ordovician mud. Small things, ordinary things, seeds of a revolution that would take 100 million years to fully unfold. The green invasion had begun, but plants were not the only pioneers testing the boundary between sea and land. The same moist rocks that hosted liverworts and fungi also attracted visitors from the water. Small creatures with jointed legs, creatures whose descendants would eventually fill the terrestrial world with movement and sound. The first animals were following the plants onto shore. They left tracks in the sand. 450 million years ago, on a beach that no longer exists, something crawled out of the water and walked across wet sediment. It left a trail, paired impressions, the marks of jointed legs pressing into the surface, a record of movement that would be buried, lithified, and preserved until someone found it and understood what it meant. The tracks are called protichnites. They appear in Ordovician sandstones from North America, from rocks deposited along the margins of ancient seas. Each trackway consists of two parallel rows of small impressions, sometimes with a central groove where a body or tail dragged across the surface. The pattern is unmistakably arthropod. No other body plan produces such regular, paired markings. Something with an exoskeleton and jointed appendages made these tracks. Something ventured onto land. The trackmaker is unknown. Protichnites could have been made by any of several arthropod groups. Eurypterids emerging from the shallows, early myriapods testing the shore, crustaceans foraging in the intertidal zone. The body fossils that would identify the trackmaker have not been found in association with the tracks. The animal remains anonymous, known only by its footprints, a ghost defined by the impressions it left behind. The anonymity does not diminish the significance. An animal walked on land in the Ordovician. That fact alone rewrites the history of terrestrial life. The sea was safe. The land was hostile. An arthropod crawling from water to air faced immediate physiological crisis. Gills, which extract dissolved oxygen from water, collapse in air, their delicate filaments clumping together, their surface area reduced to uselessness. An aquatic arthropod on land begins suffocating within minutes. The solution, book lungs, tracheae, other air-breathing structures, would evolve eventually, but the earliest land pioneers had no such adaptations. They were aquatic animals making temporary excursions, returning to water before respiration failed. Desiccation was equally threatening. Water evaporates from exposed surfaces, and an animal covered in permeable cuticle loses moisture rapidly in air. The waxy, waterproof cuticles that characterize modern terrestrial arthropods evolved over millions of years. Early land visitors had only partial protection, their excursions limited to moist environments, to humid conditions, to the hours after rain when the air itself was saturated. Weight posed another challenge. Water supports bodies. An animal neutrally buoyant in the ocean feels no strain from its own mass. That same animal on land must suddenly bear its full weight on legs evolved for swimming or walking on soft sediment. The structural reinforcement needed for terrestrial locomotion, stronger leg joints, more robust exoskeletons, modified muscle attachments, developed gradually, each generation slightly better adapted than the last. The early land arthropods solved none of these problems completely. They managed them, temporarily, incompletely, surviving brief forays before retreating to the water. The shore was a frontier, not a home. Why leave the water at all? The question has no single answer. Different lineages probably had different motivations, different ecological pressures pushing them toward the boundary between environments. Some possibilities emerge from the fossil record and from studies of modern amphibious arthropods. Food may have been the primary attraction. The intertidal zone accumulated organic debris, dead algae, stranded organisms, detritus washed up by waves. An animal that could tolerate brief exposure could exploit resources unavailable to purely aquatic competitors. The earliest terrestrial ecosystems were probably based on such detrital feeding, scavenging rather than grazing, consuming what the sea discarded. Escape from predators may have driven some excursions. The Ordovician seas were dangerous, patrolled by cephalopods and eurypterids and other predators. An animal that could leave the water, even temporarily, found refuge in an environment where those predators could not follow. The land was hostile, but it was also empty. No hunters prowled the beaches, no jaws waited among the rocks. Reproduction may have played a role. Some modern arthropods lay eggs above the waterline, protecting them from aquatic predators, from fungal infections that thrive in water, from the hazards of the marine environment. If Ordovician arthropods did the same, their reproductive biology would have selected for adults capable of terrestrial excursions, at least long enough to deposit eggs in safe locations. The pressures combined and reinforced each other. Once some individuals began exploiting land, selection favored those better adapted to survive there. Each generation pushed the boundary slightly further, tolerating longer exposures, venturing further from the water, adapting more completely to an environment that had been closed to animal life for 4 billion years. The fossil record of Ordovician land animals is frustratingly sparse. Tracks exist, protichnites and similar trace fossils indicating arthropod presence on land. Body fossils are almost entirely absent. The conditions that preserve terrestrial organisms are rare. An animal that dies on land is exposed to decay, to scavengers, to weathering, to all the destructive forces that operate above water. Only exceptional circumstances, rapid burial, anoxic conditions, permineralization, preserve terrestrial bodies, and those circumstances were uncommon in Ordovician continental environments. The Silurian and Devonian would eventually yield spectacular terrestrial fossils: millipedes, scorpions, early insects, the first arachnids. These later fossils show that terrestrial arthropods were diverse and well established by the end of the Silurian, implying that the colonization process had been underway for tens of millions of years. The Ordovician tracks are consistent with this timeline, suggesting that the first tentative steps onto land occurred during the period, even if the animals making those steps left no preserved bodies. Molecular evidence supports early colonization. Comparisons of DNA sequences among living arthropods suggest that the major terrestrial lineages, myriapods, arachnids, hexapods, diverged from marine ancestors during the Ordovician or early Silurian. The molecular clocks are imprecise, their calibrations uncertain, but they consistently point toward an Ordovician origin for terrestrial animal life. The evidence converges: tracks without bodies, molecular dates without fossils, inferences without direct proof. The picture is incomplete, fuzzy, frustrating. Yet the outline is clear enough. Animals began moving onto land during the Ordovician, following the plants that had preceded them, beginning the colonization that would eventually produce every terrestrial ecosystem on Earth. The partnership between plants and animals was not immediate. The first land plants were low-growing, hugging moist surfaces, producing little structure that animals could exploit. A liverwort offers no shelter, no elevated perch, no complex habitat. The early terrestrial environment was simple: microbial mats, patches of primitive vegetation, bare rock between them. There were no forests to inhabit, no leaf litter to hide in, no canopy to climb. Animals and plants would co-evolve over the following periods, each group creating opportunities for the other. Plants would grow taller, creating vertical structure that animals could exploit. Animals would become herbivores, feeding on plant tissue, evolving mouthparts specialized for cutting and grinding vegetation. Plants would develop defenses, toxins, thorns, tough fibers, and animals would evolve countermeasures. The arms race would drive both groups toward greater complexity. The Ordovician knew none of this complexity. The land was simple, sparse, a world in its earliest stages of biological development. The arthropods that crawled across Ordovician beaches found little to eat beyond whatever the sea had left behind. They were pioneers on a frontier that offered more hardship than reward, more danger than opportunity. Yet they persisted. Generation after generation, some individuals ventured onto land, survived long enough to reproduce, left offspring slightly better adapted than themselves. The process was slow, operating over millions of years, but it was inexorable. Life had found the continents. It would not surrender them. You can visit beaches today where the Ordovician pattern repeats. Horseshoe crabs emerge from the water to lay eggs in the sand, their ancient body plan unchanged for hundreds of millions of years. Ghost crabs scuttle between burrows, their gills modified to function in air but still requiring periodic immersion. Hermit crabs venture above the tide line, exploring the boundary between marine and terrestrial worlds. Each of these animals reenacts the transition that began in the Ordovician, demonstrating the behaviors and physiological tolerances that made colonization possible. The beaches are living laboratories, natural experiments in the water-to-land transition. The challenges faced by modern amphibious arthropods, desiccation, respiration, weight, are the same challenges the Ordovician pioneers faced. The solutions are the same: staying near water, avoiding the heat of midday, seeking humid microhabitats, retreating when conditions become intolerable. The playbook was written 450 million years ago. Modern animals still follow it. The transition from sea to land is not a single event, but a process, a gradient of adaptation that can be frozen at any point. Some animals have crossed the boundary completely, their descendants wholly terrestrial, their bodies fully adapted to life in air. Others remain on the threshold, still dependent on water for some functions, still tied to the interface between environments. The Ordovician tracks record an early stage of that process, a moment when the first animals were testing the boundary, finding it permeable, beginning to cross. The land was changing. What had been bare rock and microbial film was becoming something else, a thin veneer of life, patchy and sparse but undeniably present. Plants clung to moist surfaces, fungi threaded through crevices, Arthropods left tracks in sand that would become stone. The continents were no longer sterile. They had been colonized, claimed, transformed in ways that would only accelerate in the ages to come. The colonizers could not have known what was approaching. From their perspective on the ground, among the rocks and primitive plants, the sky was simply the sky. Blue or grey, clear or clouded, the same sky that had arched over the earth for billions of years. They could not have seen what was gathering in that sky, could not have understood the debris field that was slowly spreading around their planet. High above the crawling arthropods and the rooted plants, something extraordinary was taking shape. The Earth was growing a ring. Andy Tompkins was not looking for rings. He was looking at craters, impact craters specifically, the scars left when asteroids or comets collide with Earth, excavating holes kilometers across, vaporizing rock, leaving geological signatures that persist for hundreds of millions of years. Tompkins, a geologist at Monash University in Melbourne, had been studying the Ordovician impact record as part of a broader research program on asteroid bombardment through geological time. The numbers seemed ordinary at first. 21 confirmed impact craters from the Ordovician period, scattered across different continents, deposited over 42 million years. The distribution looked random, unremarkable, exactly what you would expect from space debris arriving from random directions at random times. Then Tompkins plotted them on a paleogeographic map. The map showed the Earth as it had existed in the Ordovician, continents arranged in their ancient configurations, before plate tectonics had shuffled them into modern positions. Laurentia at the equator, Gondwana in the south, Baltica and Siberia scattered between. The usual reconstruction, familiar to anyone who works with deep time. The craters were not scattered randomly. They fell along a line, a band running across the map from west to east, hugging the equator with precision that seemed impossible to attribute to chance. Every single confirmed Ordovician impact, 21 craters deposited over millions of years, had struck within 30 degrees of the paleo-equator. Most were within 15 degrees, several were within 5. Tompkins ran the statistics. The probability of such clustering occurring by chance was approximately 1 in 25 million. Something had confined the impacts to the equator. Something had acted like a target, drawing space debris toward a specific latitude, creating a bombardment pattern that could not be explained by random arrivals from the asteroid belt or Kuiper belt or any other source in the solar system. In September 2024, Tompkins and his colleagues published their hypothesis in the journal Earth and Planetary Science Letters. The paper was titled Evidence for a Massive, Short-Lived Planetary Ring System Around Earth During the Ordovician Period. Earth had rings. Like Saturn, like Jupiter, like Uranus, the Earth had possessed a ring system for tens of millions of years during the Ordovician, and those rings had rained debris onto the planet in a concentrated equatorial bombardment that left craters from Australia to Sweden, all aligned along latitudes that had once sat beneath a Saturn-like halo of shattered rock. The hypothesis was extraordinary. The evidence was compelling. The implications were staggering. The story began with an asteroid. Sometime around 466 million years ago, in the early Middle Ordovician, when the GOBE was transforming marine ecosystems, when trilobites carpeted the seafloors and giant cephalopods hunted the water column, an asteroid approached Earth from the inner solar system. It was large, perhaps several kilometers across, composed primarily of a type of stony meteorite called L-chondrite. These are common asteroids, accounting for about 38% of meteorites that fall to Earth today. Their compositions characterized by relatively low iron content and specific mineral assemblages that make them easy to identify. The asteroid was not heading for a collision. Its orbit was carrying it past Earth, close but not close enough for impact. A near miss, the kind of gravitational encounter that happens routinely in the solar system, usually without consequence. This time, there were consequences. As the asteroid passed within a critical distance from Earth, a boundary called the Roche limit, tidal forces began to tear it apart. The side facing Earth felt stronger gravitational pull than the far side. The differential stress exceeded the asteroid's tensile strength. The rock fractured, fragmented, disintegrated into a cloud of debris ranging from house-sized boulders to grains of dust. The Roche limit is named for Édouard Roche, the 19th century French astronomer who calculated that any object held together primarily by its own gravity will break apart if it approaches a more massive body too closely. The exact distance depends on the densities of both objects. For a rocky asteroid approaching Earth, the critical distance is approximately 9,500 kilometers from Earth's center, about 3,000 kilometers above the surface. The asteroid crossed that threshold and shattered. Most of the debris continued on diverging trajectories, scattering into orbits that would eventually carry fragments away from Earth. Some pieces fell immediately, plunging through the atmosphere, impacting the surface, creating craters. A substantial fraction, perhaps the majority of the shattered asteroid's mass, entered orbit around Earth, circling the planet in a ring of debris that extended across thousands of kilometers of space. Earth had acquired a ring system. The physics of planetary rings are well understood. Saturn's rings have been studied for 4 centuries, since Galileo first observed them through his telescope in 1610, mistaking them for ears on the planet. Modern spacecraft, Pioneer, Voyager, Cassini, have examined Saturn's rings in exquisite detail, measuring their composition, tracking their dynamics, observing how they evolve. Jupiter, Uranus, and Neptune all possess ring systems, smaller and fainter than Saturn's but governed by the same principles. All rings share certain characteristics. They orbit in the equatorial plane of their planet, confined by gravitational forces to a flat disk aligned with the planet's rotation. They are composed of particles ranging from dust grains to boulder-sized chunks, each particle following its own orbit, the collective behavior producing waves, gaps, and structures visible from space. They are temporary features on geological timescales, slowly spreading outward, falling inward, dissipating over millions of years through collisions, atmospheric drag, and gravitational perturbations. Earth's ring would have followed the same patterns. A disk of debris circling the equator, visible from the surface as a bright band stretching across the sky, brightest at dawn and dusk when sunlight illuminated the particles at optimal angles. The ring would have been spectacular, brighter than Saturn's rings appear from Saturn's surface, because Earth's ring would have been closer, denser, composed of fresher material that had not yet darkened with age. From the equator, the ring would have appeared as a narrow line bisecting the sky, arcing from horizon to horizon, too thin to show much width, but brilliant enough to outshine the Milky Way. From higher latitudes, 30 degrees north or south, the ring would have been visible as a broader band, its edge-on appearance transformed into an angled view that revealed its disc-like structure. From the poles, an observer could have looked down on the ring system, seeing it spread in a circle around the planet, a halo of light surrounding the Earth like a crown. No human observer existed to witness this. The view was wasted on trilobites and cephalopods, and organisms incapable of wonder. The ring shone in skies that no eye had evolved to appreciate, a spectacle playing to an audience of filter feeders and deposit feeders and creatures whose sensory worlds were limited to chemical gradients and touch. The ring did not last forever. Nothing in planetary dynamics lasts forever. Over millions of years, the orbiting debris gradually fell from the sky. Atmospheric drag pulled the smaller particles downward, where they burned up as meteors, adding their mass to the upper atmosphere in a gentle rain of vaporized rock. Larger pieces survived atmospheric entry, impacting the surface, excavating craters that would preserve the record of the bombardment for hundreds of millions of years. The impacts were not evenly distributed. Objects in equatorial orbit fall to Earth at equatorial latitudes. The physics allows no other outcome. A particle orbiting the equator will eventually intersect the surface at some equatorial location, pulled down by atmospheric drag, by gravitational perturbations, by the slow decay of its orbit. A ring around Earth's equator could only produce impacts on the equatorial surface. This is what Tompkins had discovered. The 21 Ordovician craters were not randomly distributed because they were not produced by random arrivals from deep space. They were ring debris, fragments of a shattered asteroid that had orbited Earth for millions of years before finally falling as a concentrated bombardment along latitudes that happened to lie beneath the ring system. The evidence supporting this hypothesis extends beyond the crater distribution. Marine sediments from the Ordovician contain elevated concentrations of L-chondrite material. The sediments accumulated on seafloors worldwide, slowly burying the organic remains of brachiopods and trilobites and graptolites, and mixed with those biological materials was extraterrestrial debris, chromite grains, platinum group elements, mineral assemblages diagnostic of L-chondrite composition. The concentrations peak in the Middle Ordovician, exactly when the ring system would have been raining material onto the planet. The spike is called the Ordovician meteor event. It appears in deep-sea sediments from dozens of locations, a global signature of enhanced meteorite infall that lasted for tens of millions of years. Previous researchers had documented this spike, had recognized it as evidence of unusual bombardment, had proposed various explanations involving collisions in the asteroid belt or the breakup of a large meteoroid. Tompkins's hypothesis provided a mechanism. The debris was not arriving from the asteroid belt, but from orbit. The gradual decay of a ring system that was dumping its mass onto the surface at a rate many times normal background levels. The duration fits. Planetary rings dissipate over millions of years, not thousands or billions. Saturn's rings are thought to be young, perhaps only a few 100 million years old, possibly much younger. And they are losing mass steadily, their particles spiraling inward or escaping outward, the whole structure slowly vanishing. Earth's Ordovician ring would have followed a similar trajectory, lasting perhaps 20 to 40 million years from formation to complete dissipation, matching the duration of the Ordovician meteor event recorded in marine sediments. The crater ages cluster in the Middle and Late Ordovician, between roughly 465 and 450 million years ago. The distribution is not uniform. More craters appear in the earlier part of this interval, suggesting that impact rates were highest shortly after ring formation and declined as the ring dissipated. This is consistent with ring dynamics, where initial conditions produce high densities of large particles that gradually thin out as the system evolves. You could have seen the ring from the surface. Stand on an Ordovician beach, Laurentia's tropical shores, Gondwana's temperate coasts, and look up. The sky is clear, the sun setting, the light fading from blue to indigo. As darkness gathers, a line of brightness appears, bisecting the heavens, running east to west, narrower than a finger held at arm's length, but brighter than any star. The ring, a band of orbiting debris catching the last rays of sunlight, glowing in the twilight, visible for hours after sunset, reappearing before dawn. The moon rises, its light dimming the ring but not erasing it. The ring is closer than the moon, brighter in some sections where particle density is higher, darker in gaps where gravitational resonances have cleared material away. The structure is complex, detailed, beautiful, if beauty can exist without observers capable of recognizing it. On some nights, meteors streak across the sky more frequently than usual. the ring debris falling at rates that temporarily spike above background levels. On rare occasions, larger pieces enter the atmosphere, producing fireballs bright enough to cast shadows, explosions loud enough to rattle the seafloor, impacts that excavate fresh craters in the tropical lowlands. The bombardment is sporadic, unpredictable, occasionally catastrophic. The ring affects climate. It must. Tompkins's paper speculates carefully, acknowledging uncertainty, but the basic physics are inescapable. A ring system blocks sunlight. The amount of blocking depends on the ring's optical depth, how much light is intercepted by particles versus how much passes through gaps. Saturn's rings have varying optical depths, some sections nearly opaque, others translucent. Earth's ring, composed of fresh rocky debris, would have been relatively opaque, particularly in its densest sections. The shadow falls on the equator. A ring orbiting Earth's equatorial plane casts its shadow on the equatorial surface, creating a band of reduced insolation, less sunlight reaching the ground, lower temperatures, altered climate patterns. The effect would be strongest at equinox, when the sun crosses the equator and shines directly through the ring plane, the shadow most concentrated. At solstice, when the sun is displaced north or south, the shadow would shift, the effect reduced but still present. The magnitude of cooling is debatable. Tompkins and his colleagues estimate that the ring might have reduced equatorial insolation by several percent, enough to lower temperatures noticeably, enough to affect ocean circulation, enough to matter to organisms adapted to the thermal stability of tropical seas. Other researchers have questioned whether the effect would be large enough to detect in the geological record, whether proxy data support cooling at the right time, whether alternative explanations might account for observed climate shifts. The debate is ongoing. The hypothesis is young, published in 2024, still being tested against evidence, still accumulating support and criticism. Science moves slowly, cautiously, requiring multiple independent lines of evidence before accepting extraordinary claims. A ring around Earth is an extraordinary claim. The evidence is mounting. The conclusion is not yet certain. What is certain is that something unusual happened in the Ordovician. The impact record is anomalous. The meteorite infall is enhanced. The crater distribution defies random explanation. Whether Tompkins's interpretation is correct, whether Earth truly had rings, whether the shadow cooled the planet, whether the climatic effects contributed to the extinction that ended the period, remains to be determined by future research. For now, the hypothesis stands as one of the most remarkable proposals in recent planetary science. Earth, for a geologically brief interval, may have resembled Saturn. The sky held a ring. The equator felt its shadow. The rocks remember the impacts, preserved in craters that waited 460 million years for someone to notice their alignment. Tompkins noticed. The pattern revealed itself to someone finally looking at the data from the right perspective, plotting craters on the right kind of map, asking the right questions. Discovery often works this way. The evidence was always there, waiting, invisible until someone looked correctly. The ring is gone now. The last fragments fell long ago, burned up in the atmosphere, cratered the surface, added their mass to the growing pile of sediment accumulating on Ordovician sea floors. What remains is inference, statistical analysis, the patient work of geologists studying crater distributions and meteorite compositions and sedimentary records. The sky was different once. A band of light arced overhead, visible from every continent, brightest at the tropics, fading toward the poles. Debris rained down for millions of years, pocking the landscape with craters, dusting the oceans with extraterrestrial material, altering the climate in ways that may have triggered catastrophe. High above the continents where arthropods were learning to breathe air, high above the seas where trilobites hunted and cephalopods prowled, the ring glowed in reflected sunlight. The particles collided, fragmented further, spiraled gradually downward. The bombardment continued, accelerated, peaked, and slowly declined as the ring thinned and vanished. The meteor storms were not over. They had barely begun. The limestone remembers. Drill a core sample from marine sediments deposited during the Middle Ordovician, rocks laid down on ancient seafloors, slowly accumulating over millions of years, and analyze the mineral composition. Among the calcium carbonate shells, among the siliceous remains of radiolarians and sponges, among the clay particles washed from distant continents, you will find something that does not belong. Chromite grains, tiny crystals of chrome iron oxide, their composition distinct from any terrestrial source, their origins unambiguously extraterrestrial. They arrived from space, embedded in meteorites, released when those meteorites vaporized in the atmosphere or fragmented on impact. They settled through the water column, accumulated on the seafloor, became incorporated into sediments that would eventually lithify into the limestones and shales that geologists now study. The concentration of chromite in Ordovician sediments is approximately 100 times higher than background levels. 100 times. Not a subtle increase, not a statistical fluctuation, not something that requires careful analysis to detect. The spike is obvious, dramatic, a signal so strong that it appears in cores from Sweden, from China, from Scotland, from Russia, from locations scattered across the planet. Wherever geologists have looked at Middle to Late Ordovician marine sediments, they have found the same pattern: enhanced concentrations of extraterrestrial material, sustained over tens of millions of years. This is the signature of the ring: debris falling from orbit, vaporizing in the atmosphere, dusting the ocean with material that had once been part of an asteroid, that had orbited Earth for millions of years, that finally rained down in quantities that overwhelmed the normal background flux of cosmic dust. The bombardment was not brief. It was sustained, intense, relentless, a meteor storm that lasted longer than the entire duration of human civilization, longer than the existence of our species, longer than most ice ages, 40 million years of fire. The numbers require context. Under normal conditions, Earth accumulates perhaps 40,000 tons of extraterrestrial material per year. Most arrives as dust, particles so small they drift gently through the atmosphere without heating, settling onto the surface as imperceptible additions to soil and sediment. Larger pieces, pebble-sized, fist-sized, burn up as meteors, visible streaks of light that astronomy enthusiasts watch during annual meteor showers. Occasionally something larger arrives, survives atmospheric entry, impacts the surface with enough energy to excavate a crater. The flux is steady, predictable, unremarkable. Space debris trickles into Earth's gravity well at a roughly constant rate, has done so for billions of years, will continue for billions more. The Ordovician broke that pattern. During the peak of the ring's dissipation, meteorite infall may have increased by a factor of 100 or more. Instead of 40,000 tons per year, perhaps 4 million tons annually, 10,000 tons per day, 400 tons per hour. Continuous delivery of space debris onto a planet whose atmosphere was not designed to absorb such quantities. The sky would have been bright with meteors, not occasionally, not during special showers when Earth's orbit crosses some comet's debris trail, but constantly. Every night would have been a meteor shower. Every clear evening would have offered a spectacle of streaking lights, fireballs, atmospheric entry signatures of material falling from the ring. Most of this material was small, grains and pebbles, fragments that burned completely before reaching the surface, adding their mass to the upper atmosphere as vapor and fine dust. The chromite grains found in sediments came from this fine material. the residue of countless small meteorites that had vaporized on entry. Each grain represented a particle that had orbited Earth, had fallen through the atmosphere, had settled through the ocean, had been buried among the shells of organisms that never knew the sky was burning. The larger pieces were more dramatic. A boulder-sized fragment entering the atmosphere releases energy equivalent to several tons of TNT. The fireball is bright enough to illuminate the landscape, to cast shadows, to be visible hundreds of kilometers away. The shockwave rattles structures, breaks windows if any structures have windows, produces sounds that carry across continents. If the fragment survives to impact, it excavates a crater, throws debris across surrounding terrain, creates a local catastrophe. During the ring dissipation, such events may have occurred monthly, weekly, perhaps even more frequently during peak periods. The planet was under bombardment, not from random arrivals from the asteroid belt, but from its own ring, from debris that was systematically clearing itself from orbit through the simple physics of atmospheric drag and gravitational decay. The craters preserve the record of the largest impacts. 21 confirmed Ordovician impact structures have been identified, all aligned along the paleo-equator, all dating to the interval when the ring was dissipating. These represent the biggest pieces, the fragments that were large enough to survive atmospheric passage, that retained enough mass and velocity to excavate craters visible in the geological record 460 million years later. The largest confirmed Ordovician crater is Lochn in central Sweden. The impact occurred approximately 458 million years ago, excavated a crater roughly 14 kilometers in diameter, released energy equivalent to several million tons of TNT. The impactor was probably between 600 meters and 1 kilometer across, a substantial asteroid by any measure, large enough to cause regional devastation, small enough that the Earth as a whole barely noticed. Lochner was not unique. Siljan, also in Sweden, is larger, 52 kilometers in diameter, though its Ordovician age has been questioned. Tveren, Granby, and numerous smaller structures scatter across Scandinavia and beyond, each one marking the arrival of a piece of the ring, each crater a scar from the bombardment. The distribution is telling. Scandinavia, or rather, the craton that would become Scandinavia, occupied near equatorial latitudes during the Ordovician. It sat beneath the ring, directly in the path of falling debris, receiving a disproportionate share of impacts. Other equatorial regions show similar patterns. Australia, positioned near the equator during the period, contains several Ordovician craters. North America, its ancient core straddling the tropics, bears impact structures from the same interval. The bombardment was not random. It could not be random. Random impacts from the asteroid belt would show no latitudinal preference, would crater the planet from pole to pole with equal probability. The equatorial concentration is a signature of ring debris, of material falling from orbits that could only intersect the surface at equatorial latitudes. The organisms living through this bombardment could not have understood what was happening. A trilobite crawling across an Ordovician seafloor, a cephalopod hunting in the water column, a brachiopod filtering particles from the current. None possessed the cognitive capacity to recognize patterns in the sky, to notice that meteors appeared more frequently than they once had, to connect the bright streaks overhead with the occasional impacts that shook the seafloor and sent tsunamis racing across shallow seas. They experienced the effects without comprehending the cause. Increased sediment flux from atmospheric dust altered light levels if the dust accumulated sufficiently, occasional catastrophes when nearby impacts disrupted their environments. The ring's dissipation was a chronic stress, a sustained perturbation of normal conditions, playing out over timescales too long for any individual organism to perceive but short enough to appear in the geological record as a distinct event. The marine sediments accumulated the evidence, Seafloors in the Ordovician were sites of continuous deposition. Shells of dead organisms, fecal pellets from zooplankton, clay particles from continental weathering, calcium carbonate precipitating from seawater, all of this settled constantly, building layers that recorded the passage of time. The chromite grains fell with everything else, mixing into the sediment, becoming part of the geological record. The concentration peaked in the Middle Ordovician and declined thereafter. Early studies of this pattern, conducted before Tompkins proposed his ring hypothesis, interpreted the chromite spike as evidence of an asteroid collision in the main belt, the L-chondrite parent body breaking up, sending fragments toward the inner solar system, some fraction eventually intersecting Earth's orbit. This explanation accounted for the enhanced meteorite flux, for the sustained duration of the event, for the L-chondrite composition. Tompkins's hypothesis adds a crucial detail. The debris did not arrive directly from the asteroid belt. It was captured into orbit first, formed a ring, spent millions of years circling Earth before finally falling. The ring explains the equatorial crater alignment, explains the sustained flux better than direct arrival could, provides a mechanism for concentrating impacts in a narrow latitude band. The evidence supports this refinement. The chromite spike begins slightly before the first confirmed craters appear, consistent with ring formation preceding the major impacts. The crater ages span the interval when chromite concentrations are highest, consistent with both phenomena being driven by ring dissipation. The pattern makes sense only if the debris orbited Earth rather than arriving directly from space. The sky was different then, more dangerous, more spectacular, more filled with reminders that space is not empty, that planetary systems contain debris, that orbits decay and gravity pulls relentlessly downward. Stand on an Ordovician shore during the peak of bombardment. The sun sets, darkness gathers, the ring appears, that familiar band of light bisecting the sky, brighter tonight because fresh material has been added, dimmer in sections where particles have recently fallen. As full night arrives, meteors begin to streak, one every few minutes at first, then more frequently, some faint and brief, others bright enough to illuminate the landscape for seconds. A few so brilliant they cast multiple shadows, their light reflecting off the shallow seas that cover the drowned continents. The display continues for hours. Some meteors are fragments of the ring, decaying orbits finally bringing them into contact with the atmosphere. Others are secondary debris, particles knocked from the ring by collisions, their trajectories randomized by impacts that shatter larger pieces into swarms of smaller ones. The physics of ring dynamics creates cascades. Collisions produce debris, debris collides with other ring material, collisional fragments decay faster than intact pieces, the whole system accelerating its own demise. The process feeds on itself. More collisions mean more small fragments. More small fragments mean higher surface area to mass ratio. Higher surface area means stronger atmospheric drag. Stronger drag means faster orbital decay. The ring dissipates exponentially once the process begins, its lifetime measured in millions rather than billions of years, its final phases potentially spectacular as the remaining material crashes down in an accelerating cascade. Whether the Ordovician witnessed such a finale remains unknown. The crater record shows no obvious spike at any particular time, no sudden burst of impacts that would indicate catastrophic ring collapse. The dissipation appears gradual, spread over tens of millions of years, a slow rain rather than a sudden storm. Perhaps the ring simply thinned until the remaining material was too sparse to produce noticeable effects, the last particles falling unrecorded, unnoticed, adding their mass to the background flux of cosmic dust. The bombardment ended. The chromite concentrations in sediments returned to normal levels by the Late Ordovician. The last confirmed impact craters from the ring dissipation period date to approximately 450 million years ago. The sky cleared, the ring faded from view, its particles gone, its shadow lifted, its 40 million year presence in Earth's sky concluded. What remained was geological memory, chromite in limestone, craters aligned along ancient latitudes, enhanced concentrations of platinum group elements in marine sediments, the subtle chemical and physical signatures that allow geologists, hundreds of millions of years later, to reconstruct what happened, to recognize the pattern, to propose hypotheses that would have seemed absurd before the evidence demanded them. Earth had rings. The rings dissipated. The sky burned for 40 million years. The rocks remember what no living thing witnessed with understanding, what no observer recorded except through the passive accumulation of debris in sediments and the excavation of craters in stone. The meteor storms finally subsided, the last fragments fallen, the chromite concentrations declining toward background levels. The sky was clearing, the ring nearly gone, only the faintest wisps of debris remaining in orbits that would decay over the next few million years. Yet the ring's most profound effect may not have been the bombardment at all. Something else was happening, something that would alter the climate of the entire planet. The shadow was cooling the world. Light does not reach everywhere. A ring orbiting Earth's equator casts a shadow on the equatorial surface. The geometry is unavoidable, fixed by the physics of orbital mechanics and the propagation of light. The sun shines from various angles throughout the year, high in the sky at equinox when it crosses the celestial equator, displaced north or south at solstice. But at equinox, the sun passes through the ring plane, and the shadow falls directly on the surface below. The shadow is not absolute. Saturn's rings, observed from Saturn's cloud tops, cast shadows that are complex and structured, with bright bands where gaps allow sunlight through, dark bands where opaque sections block the light. Earth's Ordovician ring would have shown similar structure, regions of higher and lower optical depth, variations in shadow intensity depending on local particle density. The average effect was reduction, less sunlight reaching the equatorial surface, lower temperatures in the regions directly beneath the ring, altered atmospheric circulation patterns as the thermal gradient between shadowed equator and illuminated mid-latitudes drove winds, affected ocean currents, redistributed heat in ways that no climate model can fully reconstruct from the fragmentary evidence available. The magnitude remains debated. Tompkins and his colleagues estimate that the ring might have reduced equatorial solar insolation by a few percent, perhaps 2 to 5%. Enough to lower surface temperatures by 1 or 2 degrees Celsius in the most affected regions. Other researchers have suggested larger effects, others smaller. The uncertainty is substantial because the relevant parameters are poorly constrained. The ring's optical depth, its radial extent, the size distribution of particles, the duration of maximum shadowing. What seems clear is that some cooling occurred. The climate record of the Ordovician shows a transition from greenhouse warmth to cooler conditions through the Middle and Late Ordovician. Oxygen isotope ratios in fossil shells, which record the temperature of the water in which those shells formed, indicate progressive cooling. Carbon isotope excursions suggest changes in ocean circulation and biological productivity. Sedimentological evidence points to increasing glaciation, culminating in the Hirnantian glaciation at the very end of the period, one of the most severe ice ages in Earth's history. The question is whether the ring's shadow contributed to this cooling, whether the reduction in equatorial insolation was sufficient to trigger climate feedbacks that amplified the initial effect, driving the planet toward glaciation. Whether the ring, intended by no one and controlled by nothing except gravity and orbital mechanics, inadvertently altered the course of Earth's climate history. The hypothesis is speculative. Tompkins acknowledges this explicitly in his 2024 paper. The connection between ring shadow and climate cooling is plausible, consistent with what we know about planetary energy balance, supported by the timing. The ring dissipated over the same interval when cooling was occurring. Yet proving causation from correlation is difficult, perhaps impossible, when the events occurred nearly 500 million years ago and the evidence is indirect. Climate is complex. Many factors influence global temperature. The Ordovician cooling could have resulted from changes in atmospheric carbon dioxide, from shifts in ocean circulation, from the weathering effects of newly uplifted mountains, from the early land plants that were beginning to colonize the continents and alter the carbon cycle. The ring shadow could have been one factor among many, a contributing cause rather than the sole driver, part of a confluence of conditions that together pushed the climate system toward a new state. Disentangling the contributions of multiple factors is a challenge that climate scientists face routinely when studying recent climate change. The challenge becomes nearly insurmountable when studying climate change 450 million years ago, when direct measurements are impossible, when proxy records are sparse and ambiguous, when the configuration of continents and oceans was radically different from the present. The shadow fell. The planet cooled. Whether the two phenomena were connected causally or merely coincidentally remains an open question. Consider the physics of equatorial shadowing. The equator receives the most direct sunlight of any latitude. The sun passes nearly overhead at midday, its rays striking the surface at close to 90 degrees, delivering maximum energy per unit area. This is why tropical regions are warm, why rainforests cluster near the equator, why the equatorial oceans are the warmest on the planet. Remove even a fraction of that incoming solar energy, and the thermal balance shifts. Atmospheric circulation is driven by temperature gradients. Warm air rises, cool air sinks. The resulting pressure differences generate winds. In the tropics, warm air rises at the equator and flows poleward at altitude, cooling as it moves, eventually sinking at subtropical latitudes around 30 degrees north and south. This circulation pattern, the Hadley cells, transports heat from equator toward poles, moderates temperature extremes, drives the trade winds that sailors have relied upon for centuries. Cooling the equator weakens this circulation. If the equatorial surface receives less energy, the air above it warms less, rises less vigorously, transports less heat poleward. The whole atmospheric engine runs at lower power, the winds slow, the heat transport diminishes. Mid-latitudes receive less warmth from the tropics and cool in response. The effect cascades through the climate system. Ocean circulation responds similarly. Warm water at the equator expands, creating a slight bulge in sea level, driving surface currents away from the equator. Cool the equatorial ocean, and the bulge flattens, the currents weaken, the poleward heat transport decreases. Less heat reaches high latitudes. The poles cool further. Ice begins to accumulate. Ice has high albedo. It reflects sunlight rather than absorbing it. A planet with more ice cover reflects more solar energy back to space, cools further, forms more ice, reflects even more sunlight. The ice albedo feedback is one of climate science's most powerful amplifiers, capable of driving a planet from temperate conditions to full glaciation once the process begins. The Ordovician ended in ice. The Hirnantian glaciation, named for the Hirnant Valley in Wales, saw massive ice sheets develop on Gondwana, which by then had drifted over the South Pole. Sea levels dropped by perhaps 70 to 100 meters as water was locked in ice. Shallow tropical seas retreated from the continents they had flooded. Marine ecosystems, which had been thriving in warm, stable conditions for tens of millions of years, faced environmental stress on a global scale. The extinction followed. The Late Ordovician Mass Extinction, the second largest in the Phanerozoic, eliminated roughly 85% of marine species. Trilobites suffered catastrophic losses. Brachiopods declined dramatically. Graptolites were decimated. The carefully constructed tiered communities that had characterized Ordovician seafloors disintegrated. Their component species driven extinct by cooling, by habitat loss, by the cascade of ecological disruptions that followed the climate shift. Could the ring shadow have contributed to this catastrophe? Could the decades or centuries of reduced solar heating at the equator have been sufficient to tip the climate system into glaciation? The timing is suggestive. The ring dissipated over the middle to late Ordovician, with the most intense shadowing probably occurring during the peak of the ring's mass and optical depth. The Hirnantian glaciation occurred at the very end of the Ordovician, perhaps 10 to 15 million years after the ring's final dissipation. The lag is substantial. If the ring caused the cooling, the effect was delayed, mediated through slow feedbacks in the climate system. Ocean thermal inertia could explain such a lag. The ocean holds enormous amounts of heat and changes temperature slowly. A sustained reduction in equatorial solar heating would cool the surface ocean relatively quickly, within decades or centuries, but cooling the deep ocean takes much longer. The full climatic response to reduced insolation might not manifest for millions of years as the ocean's heat content gradually equilibrates to the new energy balance. Carbon cycle dynamics introduce additional delays. If equatorial cooling affected biological productivity, altered the weathering rates on continents, changed the burial rate of organic carbon in marine sediments, the atmospheric carbon dioxide concentration would shift on timescales of hundreds of thousands to millions of years. A decrease in CO2 would amplify the cooling initiated by the ring shadow, driving the climate system toward glaciation through a mechanism that lagged far behind the original forcing. The hypothesis is plausible but unproven. It may be unprovable. Climate attribution is difficult enough for events that occurred decades ago, with comprehensive instrumental records and sophisticated models. Attempting attribution for events that occurred hundreds of millions of years ago, with sparse proxy data and limited ability to constrain boundary conditions, approaches the limits of what science can confidently determine. What remains is a story that fits the available evidence without contradicting any of it. The ring formed, shadowed the equator, dissipated over tens of millions of years. The climate cooled during this interval. The cooling culminated in glaciation. The glaciation triggered mass extinction. The causal chain connecting these events is speculative but not implausible, suggestive but not proven, the kind of hypothesis that future research might support or refute as new data become available. The shadow is gone now. The ring dissipated 450 million years ago. Its last particles fallen. Its shadow lifted. The equatorial surface once again receiving full sunlight. The cooling that followed, whether caused by the ring or merely coincident with it, transformed the planet, ended the Ordovician, set the stage for the recovery that would unfold in the Silurian. The organisms that survived the glaciation could not have known what they had endured. They experienced the effects without understanding the causes, adapted to changing conditions, without comprehending the forces reshaping their world. A trilobite clinging to life in cooling waters, a brachiopod filtering increasingly frigid seas, a graptolite colony drifting through an ocean whose thermal structure was being revolutionized. None possessed the capacity to look up, to see the shadow, to connect the ring's presence with the climate's transformation. They lived through it. Most did not survive it. The extinction was merciless, eliminating species that had persisted for tens of millions of years, families that had survived previous environmental shifts, entire ecological guilds that had seemed permanent features of marine ecosystems. The warm, stable seas of the Middle Ordovician gave way to the cold, fluctuating conditions of the Late Ordovician, and the organisms adapted to warmth had no time to evolve the tolerances that survival required. The shadow teaches a lesson about planetary fragility. Earth's climate is sensitive to perturbations, responsive to changes in energy balance that might seem small in absolute terms, but are large relative to the system's stability margins. A few % reduction in solar insolation, sustained over millions of years, amplified by feedbacks that magnified the initial effect, sufficient to trigger glaciation, to drive extinction, to fundamentally reorganize the biosphere. The ring was an accident. No cosmic intelligence placed it in orbit. No purpose governed its formation or its dissipation. A single asteroid passed within the Roche limit, shattered, entered orbit, rained debris onto the surface for 40 million years, and vanished. The shadow it cast may have cooled the planet enough to end an entire geological period. Such are the contingencies of planetary history. Small events, an asteroid passing slightly closer than usual, produce large consequences through chains of causation too complex to predict, too dependent on initial conditions to ever repeat exactly. The Ordovician was unique. The ring was unique. The cooling, whether caused by the ring or not, was unique. No other period in Earth's history offers a clear parallel. Yet the mechanisms are universal. Shadows cool surfaces. Cooling triggers feedbacks. Feedbacks amplify initial perturbations. Climate systems can shift states rapidly once thresholds are crossed. These principles apply equally to the Ordovician and to the present, to a planet with rings and to a planet warming under enhanced greenhouse forcing. The shadow fell, the world cooled, the ice came. And when the ice came, 85% of marine species could not endure what followed. The Ordovician was ending. The warm, flooded world with its tiered communities and giant predators and trilobite-covered seafloors was collapsing into something colder, harsher, less forgiving. The greatest mass extinction since the Cambrian was beginning. Gondwana was drifting south. The supercontinent had been moving for tens of millions of years, carried by plate tectonics at rates measured in centimeters per year, imperceptible to any organism living through the motion, obvious only from the perspective of geological time. During the early Ordovician, Gondwana had straddled the southern tropics and temperate zones, its margins lapped by warm seas, its interior largely submerged beneath shallow tropical waters. By the late Ordovician, the drift had carried a substantial portion of the landmass over the South Pole. Land at the pole changes everything. Oceans resist freezing. Water has enormous thermal inertia, holds heat through polar winters, moderates temperature extremes. A planet with polar oceans remains relatively warm, its poles ice-free or covered only by seasonal sea ice that melts each summer. A planet with polar landmasses develops permanent ice sheets, glaciers that persist year-round, ice caps that grow during cool periods and resist melting even when temperatures rise. Gondwana provided a platform for ice. The South Pole, which had been open ocean through most of the Ordovician, was now solid ground. Snow fell in winter and did not entirely melt in summer. Year after year, the accumulation continued, compressing previous year's snowfall into ice, building glaciers that spread from the highlands, ice sheets that eventually covered millions of square kilometers. The Hirnantian glaciation had begun. Named for the final stage of the Ordovician period, it was brief by geological standards, lasting perhaps several 100,000 years, possibly as long as 2 million years. But severe in its effects. Ice volumes approached or exceeded those of modern Antarctic ice sheets. Sea levels dropped by 70 to 100 meters as water was transferred from ocean to ice. Coastlines retreated, shallow seas that had covered continental interiors drained away. Organisms adapted to stable marine conditions faced rapidly changing environments. The extinction unfolded in two pulses. This detail matters. The Late Ordovician Mass Extinction, abbreviated LOME in the literature, was not a single catastrophe but a double strike. Two waves of extinction separated by perhaps a few 100,000 years, each wave eliminating different groups of organisms, the combined effect producing the second largest biodiversity loss in the Phanerozoic. The first pulse coincided with glaciation. As ice sheets expanded on Gondwana, sea levels fell, temperatures dropped, ocean circulation patterns shifted. Species adapted to warm, shallow seas found their habitats disappearing. Tropical organisms accustomed to thermal stability experienced cooling beyond their tolerance ranges. Communities that had occupied flooded continental shelves were stranded as those shelves emerged, their environments converted from marine to terrestrial in a geological instant. Graptolites suffered immediate losses. These planktonic organisms, which had diversified spectacularly through the Ordovician, saw numerous families go extinct during the first pulse. The collapse of graptolite diversity was dramatic, from more than 100 species in some regions to fewer than 20. The survivors were predominantly cool water forms, species that had evolved at higher latitudes and could tolerate the falling temperatures that tropical species could not. Brachiopods declined but did not collapse. Some families went extinct, particularly those restricted to tropical shallow water environments. Others persisted, adapting to cooler conditions or shifting their ranges toward regions where suitable habitats remained. The survivors would rebound in the Silurian, recolonizing shelves as sea levels rose and temperatures moderated. Trilobites faced catastrophic losses. Numerous families disappeared during the first pulse, their diversity crashing from Ordovician peaks toward the diminished state that would characterize the group through the rest of the Paleozoic. The trilobites had been declining since the Middle Ordovician. Competition from other arthropods, predation by cephalopods and eurypterids, ecological changes as communities reorganized. But the glaciation accelerated their fall. After the LOME, trilobites would never again dominate marine ecosystems. The cephalopods suffered heavily. The giant orthocones that had ruled Ordovician seas disappeared almost entirely. Endocheirus, Camaraocheirus and their relatives vanished from the fossil record, their 6-meter shells absent from post-Ordovician sediments. The ecological role of apex marine predator would eventually be filled by other groups, sharks in the Devonian, marine reptiles in the Mesozoic. But the Ordovician giants left no descendants capable of matching their size or dominance. The first pulse eliminated an estimated 61% of marine genera. This alone would have qualified as a major mass extinction. The second pulse made it catastrophic. Between the two pulses, conditions partially recovered. Glaciers retreated slightly, sea levels rose, temperatures increased. The brief interval between extinction waves, perhaps 200,000 years, perhaps longer, saw some organisms recolonize habitats, some ecosystems begin to reorganize, tentative signs of recovery. The recovery was interrupted. The second pulse occurred as glaciation ended. Ice sheets collapsed rapidly, returning their stored water to the ocean. Sea levels rose, flooding the continental shelves that had recently emerged. Temperatures warmed, particularly in the tropics, where cooling had been most severe. The environmental changes that had driven the first pulse reversed themselves in the second. Species that had survived the cooling by adapting to cooler conditions now faced warming. Species that had shifted their ranges poleward to escape tropical heat loss now found their habitats warming beyond tolerance. The survivors of the first pulse were maladapted to the recovery, vulnerable to the very processes that ended the glaciation. Anoxia developed in the oceans. As ice melted and temperatures rose, ocean stratification increased. Warm surface waters floated atop cooler deep waters, reducing vertical mixing, limiting the oxygen transport from atmosphere to depth. Bottom waters became oxygen depleted, eventually anoxic, entirely without dissolved oxygen in some regions. Organisms that lived on or near the seafloor suffocated. Communities that had survived the first pulse by retreating to deeper, cooler waters found those refugees turned lethal. Carbon isotope excursions in the geological record document these anoxic events. Organic carbon depleted in the heavy isotope carbon-13 accumulated in sediments deposited under anoxic conditions. The isotopic signature spikes during the second extinction pulse, evidence of widespread oxygen depletion, of oceans struggling to circulate, of ecosystems collapsing under stress that came not from cooling but from the warming that followed. The combined effect was devastating. 85% of marine species disappeared. Entire ecological guilds vanished. The tiered suspension feeding communities that had characterized Ordovician seafloors disintegrated. Reef-building organisms collapsed. The diversity that had accumulated over 50 million years of GOBE radiation was pruned back in less than 1 million years of environmental crisis. The extinction was selective. Deep water species fared poorly, trapped in anoxic conditions with nowhere to flee. Tropical species suffered heavily, unable to adapt quickly enough to rapid temperature changes. Specialized species with narrow environmental tolerances went extinct more readily than generalists. Organisms with planktonic larval stages, dependent on favorable ocean conditions for reproduction, faced higher extinction rates than those with direct development. Some groups emerged relatively unscathed. Bivalve mollusks, clams and their relatives, survived better than most, their ability to burrow into sediment providing refuge from unstable water column conditions. Gastropods persisted, their mobility and feeding flexibility allowing them to exploit new resources as ecosystems reorganized. Certain echinoderm groups weathered the extinction and diversified afterward, filling niches vacated by extinct competitors. The survivors inherited a depleted ocean. The Silurian world would be less diverse than the Ordovician had been, its ecosystems simpler, its communities less tightly integrated. Recovery would take millions of years, new radiations eventually restoring diversity. But the particular assemblage of organisms that had made the Ordovician distinctive was gone, replaced by something different. The causes of the loam remain debated in some details. Glaciation is clearly central. The timing is too precise, the environmental changes too consistent with ice sheet dynamics to be coincidental. The two-pulse structure, with extinctions during both cooling and warming phases, suggests that rapid climate change itself was more lethal than any particular temperature regime. Organisms can adapt to cold or heat given sufficient time. They struggle to adapt to rapid shifts from one to the other, the whipsaw of environmental conditions changing faster than evolution can track. Volcanic activity may have contributed. Arc volcanism along Gondwana's margins increased during the Late Ordovician, releasing carbon dioxide and other gases into the atmosphere. Some researchers argue that this volcanism helped end the glaciation by adding greenhouse gases that warmed the planet. Others suggest that volcanic emissions contributed to ocean acidification, adding stress to organisms already struggling with temperature and oxygen changes. The orbital mechanics of glaciation may have amplified the crisis. Ice sheets grow and collapse not smoothly but in fits and starts, driven by Milankovitch cycles, periodic variations in Earth's orbit and axial tilt that modulate the amount and distribution of solar radiation. Glaciation tends to produce oscillations, brief warm periods interrupting longer cold phases, sea levels rising and falling on cycles of tens to hundreds of thousands of years. Organisms tracking these changes, migrating as environments shift, face repeated disruptions rather than a single crisis. the cumulative stress may have been more destructive than any individual environmental change. Whatever the precise mechanisms, the outcome was clear. The Ordovician ended in catastrophe. The period that had seen the greatest marine diversification in Earth's history concluded with one of the greatest marine extinctions. The irony is profound. The GOBE created diversity that the LOME destroyed. The 50 million years of radiation undone in a fraction of that time by climate changes that organisms could not survive. The ice has melted. The glaciers that covered Late Ordovician Gondwana are gone, their deposits scattered across continents that have since drifted thousands of kilometers from the poles where the ice formed. Tillites, rocks formed from glacial deposits, mark the ice sheet's extent, their cobbles and boulders scratched by glacial transport, their matrix composed of pulverized rock flour ground beneath the weight of moving ice. You can see these tillites today in South Africa, in the Cederberg Formation, in Morocco, in the Anti-Atlas Mountains, in Bolivia, in the Candelaria Formation. The ice left its signature on rocks that now lie in subtropical or tropical latitudes, far from the poles, testament to a geography that no longer exists and a climate that 443 million years have erased. The rocks remember what the organisms could not comprehend. The ice advanced, the seas retreated, the temperatures plunged, and then, before adaptation could catch up, the ice vanished, the seas returned, the temperatures soared, and anoxia spread through oceans that had just begun to recover from the first assault. No warning, no reprieve, no time to evolve the tolerances that survival required. 85% did not make it. Their fossils mark the boundary, the thin layer of rock that separates Ordovician from Silurian, the last appearance datums that define the Lome. Above that boundary, the fossil assemblages are different, poorer, the survivors of a catastrophe that had reshaped the living world. The Ordovician had been extraordinary. 42 million years of warmth, of flooded continents, of marine diversification unmatched before or since. The seas had filled with trilobites and cephalopods, with filter feeders building tiered communities, with organisms exploring every conceivable way of making a living in an ocean. The skies had held a ring, a band of light that would never be seen again. The continents had received their first colonists, plants and arthropods, testing the boundary between water and air. All of it ended in ice. The ring's shadow may have contributed, one factor among many, a perturbation that helped tip the climate system toward glaciation. Or perhaps the shadow was irrelevant, the cooling driven by tectonics and orbital mechanics and the contingencies of continental drift. The correlation is suggestive but not conclusive, the kind of pattern that historians recognize without being able to prove causation. What remains certain is that the ice came, the extinction followed, and the Ordovician world did not survive. The period ended. The survivors began the slow work of recovery. The seas would fill again, ecosystems would reorganize, diversity would eventually return. But the Ordovician was over. The warm, flooded world had frozen and emptied. Something new was beginning. The seas were quiet. In the aftermath of extinction, the oceans held fewer voices, fewer movements, fewer organisms filling fewer niches. The seafloors that had been carpeted with trilobites, that had bristled with crinoid meadows and bryozoan forests, that had echoed with the jet propulsion of cephalopods hunting through the water column. Those seafloors were simpler now, sparser, communities reduced to their essentials, ecosystems stripped of their elaborations. The survivors were not chosen for their beauty or their complexity. They were chosen by chance, by tolerance, by the accident of possessing traits that happened to match the demands of rapidly changing environments. Some had been common in the Ordovician, others had been marginal, living in regions or depths that the dominant species had overlooked. The extinction reshuffled the deck, and when the cards settled, different groups held power. Brachiopods persisted. These bivalved filter feeders, which had been abundant through the Ordovician, survived the loam better than many groups. Their diversity declined, families went extinct, entire ecological guilds disappeared, but enough survived to recolonize the Silurian seas. The brachiopods would continue to dominate seafloors for another 200 million years, only gradually ceding their prominence to bivalve mollusks in the Mesozoic. The brachiopods that survived tended to be generalists, species with wide environmental tolerances, forms that could filter in warm or cool water, organisms capable of attaching to various substrates or living unattached on soft sediment. Specialization had been lethal. The tropical shallow water specialists, the species adapted to precise temperature ranges or specific substrates, had been eliminated. The survivors were the flexible, the adaptable, the organisms that had never committed fully to any particular lifestyle. Bivalve mollusks, the clams, expanded into spaces that brachiopods had vacated. Bivalves had been present through the Ordovician, never particularly diverse, overshadowed by their brachiopod competitors. The extinction changed their prospects. With brachiopod diversity reduced, with ecological space available, bivalves began the radiation that would eventually make them the dominant bivalved organisms in modern oceans. The transition was slow. The Silurian remained a brachiopod world, but the trajectory was set. Gastropods survived well. Snails and their relatives weathered the extinction with minimal losses, their mobility and dietary flexibility allowing them to exploit changing conditions. A gastropod can graze on algae, scavenge dead organic matter, or predate on other invertebrates. This versatility proved valuable when stable resources disappeared and opportunism became essential for survival. Crinoids survived, though their diversity was reduced. The towering meadows of Ordovician crinoids were gone, replaced by simpler communities of lower diversity forms. The survivors re-established the crinoid body plan, the stalked, filter-feeding lifestyle that had proven successful, and began the slow process of diversification that would produce the crinoid radiations of the Silurian and Devonian. Crinoids would remain important components of marine ecosystems for the next 300 million years, only declining in the Mesozoic as mobile echinoderms, starfish, sea urchins, became more diverse. Graptolites survived in reduced numbers. From more than 100 species in some Ordovician faunas, the graptolite diversity crashed to perhaps 20 species globally. The survivors were predominantly forms that had evolved in cooler waters, species whose thermal tolerances included the lower temperatures that had eliminated tropical graptolites. These survivors would diversify modestly in the Silurian, never regaining their Ordovician diversity, eventually going extinct in the Devonian when another environmental crisis eliminated the remaining planktonic forms. Trilobites survived. They had no choice. Extinction is a passive process, not an active decision. The trilobite lineages that persisted through the LOME were diminished shadows of their Ordovician ancestors. The diversity had been pruned ruthlessly. The elaborate spine-bearing forms, the giant predatory species, the specialized swimmers, most were gone. What remained were generalists, smaller forms, conservative body plans that had survived by being unremarkable. Trilobites would continue for another 200 million years. They would never again dominate. The Silurian and Devonian trilobites were secondary players, present but not prominent, filling ecological roles but not defining ecosystems. By the Carboniferous, they were rare. The Permian extinction, at the end of the Paleozoic, eliminated the last of them. The group that had persisted for nearly 300 million years that had witnessed the Cambrian explosion and the Ordovician radiation and multiple mass extinctions, finally ended. The conodonts survived. These eel-like vertebrates, whose tooth-like elements are so common in Paleozoic rocks, weathered the loam and continued through the Silurian, Devonian, Carboniferous, Permian, Triassic, a remarkable persistence that would only end with the Triassic-Jurassic extinction 200 million years ago. The conodonts left no descendants. They were an evolutionary dead end, a successful one that lasted 300 million years but produced no lineage that survives today. The armored, jawless fish, the ostracoderms, persisted in reduced numbers. These early vertebrates, which had been experimenting with bone and armor since the Ordovician, survived to continue their evolution in the Silurian. They would eventually give rise to the jawed fish, the gnathostoms, that would dominate aquatic environments thereafter. The vertebrate story, which had begun so tentatively in the Ordovician, continued in the Silurian, building toward radiations that would eventually produce everything from sharks to humans. On land, the colonization continued. The primitive plants that had established themselves on Ordovician shores persisted, their spores appearing in Silurian sediments, their presence indicating that the greening of continents had survived the marine extinction. The terrestrial arthropods, the pioneers that had left tracks on Ordovician beaches, continued their adaptation to air-breathing existence. The Silurian would see more confident colonization, more diverse terrestrial communities, the establishment of ecosystems that were genuinely terrestrial rather than merely amphibious. The recovery was slow. Diversity does not rebound quickly after mass extinction. The Silurian seas were simpler than Ordovician seas for millions of years. Ecosystems gradually reorganized, new species evolving to fill empty niches, surviving lineages radiating into available ecological space. The process took 5 to 10 million years, longer than the extinction itself had lasted, longer than modern humans have existed, a span of time that seems geological to any organism living through it, but is merely a moment in the deep time perspective of Earth's history. The recovery was incomplete in some ways. Certain ecological guilds never fully re-established. The tiered suspension feeding communities of the Ordovician, with their vertical stacking of brachiopods, bryozoans, and crinoids, never achieved the same complexity in the Silurian. Reef ecosystems rebuilt but remained simpler. The apex predator role, vacated by the giant orthocone cephalopods, remained unfilled for tens of millions of years until new groups, eurypterids in the Silurian, placoderms in the Devonian, evolved to occupy it. Yet life persisted. It always persists. Even the worst mass extinctions, events that eliminate 90% or more of species, leave survivors, and survivors reproduce, and their descendants diversify. The tree of life is pruned by extinction but never uprooted. New branches grow from the surviving stems, radiation follows extinction, diversity eventually returns to pre-crisis levels or beyond. The Ordovician survivors carried forward the innovations that the period had produced. Filter feeding in three-dimensional tiered communities, predation by mobile cephalopods, armor as defense against increasingly dangerous predators, the colonization of land by plants and arthropods. These innovations persisted, transmitted to the Silurian and beyond, becoming foundational elements of ecosystems that would characterize the rest of the Paleozoic. The extinction had selected for resilience. The organisms that survived were those capable of tolerating environmental change, of exploiting multiple resources, of persisting when conditions were unfavorable. These traits, flexibility, generalism, tolerance, would be favored repeatedly through Earth's history as subsequent extinctions pruned away specialists and selected for survivors capable of enduring disruption. The pattern would repeat. Mass extinction, survival, recovery, diversification, another mass extinction. The cycle has played out 5 times in the Phanerozoic, the Big Five mass extinctions that define major boundaries in the geological timescale. The Loam was the second. 3 more would follow. The Late Devonian extinctions, the Permian-Triassic event that nearly ended complex life entirely, the Triassic-Jurassic extinction, and the Cretaceous-Paleogene impact that eliminated the non-avian dinosaurs. Each extinction reshaped the biosphere. Each recovery produced something new. The organisms that inherited the post-extinction world were different from those that had dominated before, adapted to the new conditions, building ecosystems that incorporated lessons from the catastrophe. Evolution is shaped by extinction as much as by adaptation, the tree of life sculpted by catastrophe as much as by competition and selection. The Ordovician is still with us. Walk along a modern beach and you are walking on Ordovician limestone, the compressed shells of brachiopods and crinoids and bryozoans that lived 500 million years ago. The calcium carbonate they secreted from Ordovician seawater has been cycled through tectonic processes, weathered from uplifted mountains, transported by rivers, deposited as sand on shores that did not exist when the organisms were alive. The atoms persist. The forms are gone, but their material remains, transformed, redistributed, incorporated into the ongoing processes that shape the planet. The descendants of Ordovician survivors swim in modern oceans. Nautilus, the sole surviving genus of externally shelled cephalopods, carries forward the body plan that the Ordovician nautiloids pioneered. Horseshoe crabs, whose lineage dates to the Ordovician, crawl on modern beaches with body plans essentially unchanged for 450 million years. Brachiopods persist in deep-water environments, living fossils clinging to existence in habitats where competition is reduced and their ancient adaptations remain viable. The vertebrate lineage that began so humbly in Ordovician seas, armored jawless fish filtering organic particles from shallow waters, produced every fish that swims today, every amphibian, reptile, bird and mammal. Your backbone is an Ordovician innovation. The vertebrate body plan that supports your skeleton, that protects your spinal cord, that allows the complexity of your nervous system, was being refined in those ancient seas by organisms that had just invented bone. The ring is gone. The shadow has lifted. The ice has melted. The extinction is over. 443 million years separate us from the Ordovician, a gulf of time so vast that the mind cannot easily grasp it, cannot hold the scale without resorting to analogies that themselves require explanation. Yet the connection persists. The Ordovician produced the world we inherited. Its innovations are still in use. Its survivors' descendants are still alive. The seas are filling again in the Silurian. The seafloors are receiving their first post-extinction colonists. The plants on land are spreading. The arthropods are adapting to terrestrial existence. The survivors are radiating, exploring the empty spaces that extinction created, beginning the diversifications that will build the Silurian and Devonian worlds. The Ordovician is over. The warm, flooded seas that covered most continents are draining, their levels recovering slowly from the glacial low stand. The ring that once arched across equatorial skies has dissipated completely, its last fragments fallen, its shadow erased. The giant cephalopods that hunted through the water column are extinct, their 6-meter shells absent from Silurian sediments. The trilobite meadows that carpeted Ordovician seafloors are gone, replaced by simpler communities of surviving lineages. What remains is memory encoded in stone. Fossils preserve what lived. Sediments record what fell. Isotopes document what changed. The rocks remember the Ordovician with perfect fidelity if imperfect completeness, holding evidence that patient geologists can extract and interpret. building pictures of ancient worlds from fragments scattered through time. The story is ending now. The Ordovician has concluded. The Silurian is beginning. The seas that had been so full, so diverse, so complex are simpler now. The recovery will take time, millions of years, dozens of species radiating into hundreds, hundreds into thousands, ecosystems rebuilding their complexity layer by layer, trophic level by trophic level, the slow, patient work that life performs after catastrophe. The survivors are doing what survivors do. They persist, they adapt, they fill the spaces that opened when so much died. They carry forward the innovations that worked, abandon the specializations that failed, try new combinations that might succeed where old patterns did not. You can rest now. The extinction is over. The ice has melted. The seas are rising. Life continues, has always continued, will continue as long as liquid water and energy and the chemistry of carbon allow. The Ordovician taught its lessons about diversity, about extinction, about the fragility of ecosystems and the resilience of life itself. The warm, shallow seas are returning. The filter feeders are rebuilding their meadows. The predators are hunting. The prey are hiding. The great wheel turns. The cycle continues. The ring glowed in Ordovician skies for 40 million years, a band of light that no human eye will ever see, a spectacle witnessed only by organisms incapable of wonder. The shadow fell across the equator and may have cooled the world. The ice came to Gondwana and the seas emptied, and 85% of species did not survive. What survived carries the story forward. The Ordovician lives in its descendants, in the fossils pressed into limestone, in the innovations that became permanent features of life on Earth. The period is over. The world moved on. The survivors built something new. Sleep now. The Ordovician has ended. The seas are quiet. The survivors are rebuilding. Time moves forward. Life continues. Good night.